Did you know that every part of you once came from a star? Our universe is like a big, amazing puzzle filled with stars, galaxies, and mysteries. Let's take a trip back in time, starting with the Big Bang that made space and leading to the galaxies we see at night. We'll learn about how stars are born and die, what makes our solar system work, and even the chances of finding life somewhere else in space. Join us as we uncover the secrets of the universe, how it affects us here on Earth, and what might happen in the future. The Big Bang Theory is the leading explanation for the origin of our universe. Imagine the universe as an immensely dense and hot point, roughly the size of a grain of sand. This point contained all the energy and matter that would eventually form everything we see today. Around 13 billion years ago, this tiny speck began to expand rapidly, an event we now refer to as the Big Bang. This expansion wasn't just an explosion in space, rather, it was the expansion of space itself. In those first moments, temperatures soared to unimaginable heights, and as the universe expanded, it cooled down. This cooling allowed quarks and electrons to form. When conditions became favorable, these quarks combined to create protons and neutrons, forming the building blocks of atoms. Over millions of years, clouds of hydrogen and helium, the simplest elements created during this period, began to coalesce under gravity's influence, leading to the formation of stars and galaxies. The light we see today from distant galaxies can be traced back to this primordial event, giving us a glimpse into the universe's early moments. The Big Bang Theory also accounts for the observed abundance of these light elements and the cosmic background radiation that fills the universe, an afterglow from that early moment. This radiation serves as a snapshot of the infant universe, revealing information about its composition, temperature, and expansion. In this way, the Big Bang Theory not only explains how the universe began, but it also opens a window into the fundamental processes that continue to shape it today. The theory of cosmic inflation emerged from the need to explain certain puzzling aspects of the universe's early development. Scientists recognized that the observable universe is remarkably uniform. This means that despite vast distances between galaxies, the cosmic microwave background radiation, a remnant from a hot, dense state shortly after the Big Bang, is evenly distributed. However, this uniformity raises a question. How could regions so far apart be so similar if they had never been in contact? To address this conundrum, cosmologists proposed that an incredibly rapid expansion, or inflation, occurred just after the Big Bang. This expansion would have stretched those small, uniform regions across vast distances in a fraction of a second, smoothing out variations and creating the homogeneity we observe. Supporting evidence for inflation comes primarily from observations of the cosmic microwave background itself. Measurements from satellite missions, such as the Wilkinson Microwave Anisotropy Probe, have revealed slight temperature fluctuations in this radiation. These tiny deviations in temperature point to the quantum fluctuations in density that would have existed before inflation, which were then stretched to cosmic scales during that brief period of rapid expansion. Additionally, the large-scale structure of the universe, including how galaxies are distributed in clusters and voids, aligns well with predictions made by inflation theories. It suggests that these structures formed from the small initial inhomogeneities forged during the inflationary epoch. Finally, studying gravitational waves, ripples in space-time that are generally produced by immense cosmic events, has provided another potential layer of evidence. If inflation generated gravitational waves as theorized, future observations could validate the inflationary model even further. Thus, the theory of cosmic inflation not only began as an elegant solution to a significant question, but has also been supported by consistent observational results that fit within the framework of our understanding of the universe's evolution. The formation of the first atoms was a pivotal moment in the history of the universe, setting the stage for everything that would come after. After the Big Bang, The universe began as a hot, dense soup of particles, primarily composed of protons, neutrons, and electrons, all zipping around at incredible speeds. As the universe expanded, it started to cool down, and this cooling allowed these particles to combine and form the simplest type of atom, hydrogen. In this primordial environment, hydrogen atoms began to emerge as the first stable units of matter. These hydrogen atoms eventually clumped together under gravity, forming the first clouds of gas. As these clouds continued to gather mass, they sparked the birth of the very first stars. It's fascinating to note that these stars were mainly composed of hydrogen, and in their cores, through the process of nuclear fusion, they began to transform hydrogen into heavier elements like helium and beyond. This transition was crucial. The first stars acted as cosmic furnaces, forging new elements essential for the complexity of the universe we observe today. When these stars reached the end of their life cycles, they exploded in powerful supernovae, scattering these newly created elements throughout the universe. This widespread distribution enriched the interstellar medium, laying the groundwork for the formation of planets and eventually life. Thus, the formation of the first atoms was not merely the birth of matter, but the beginning of a chain reaction that would lead to the creation of stars, galaxies, and the vast structures we see today. It was an extraordinary leap from a hot, chaotic state to a structured universe, revealing the power of simple building blocks in shaping complex systems. The era of recombination marks a pivotal moment in the history of the universe, occurring roughly 300,000 years after the Big Bang. During this time, the universe had expanded and cooled to the point that electrons could combine with protons to form neutral hydrogen atoms. Before this phase, the universe was a hot, dense plasma filled with free electrons and protons, creating a fog that light could not penetrate. As temperatures fell, these electrons found their place in stable orbits around protons, allowing photons, light particles, to travel freely. This transition is significant because it made the universe transparent for the first time, allowing light to move without scattering. This light would eventually become what we know today as the cosmic microwave background radiation, a faint glow that fills the universe and provides us a snapshot of its early state. The impact of the era of recombination on cosmic evolution is profound. It set the stage for the formation of the first structures in the universe. Once matter became neutral, it could begin to clump together under the influence of gravity. This led to the formation of primordial gas clouds, which would eventually evolve into the first stars and galaxies. The release of the cosmic microwave background radiation also had important implications for cosmology. By studying this radiation, scientists can gather information about the conditions of the early universe and the rate of its expansion. Additionally, this era helped establish the large-scale structure of the cosmos, influencing how galaxies and galaxy clusters formed over billions of years. Essentially, the era of recombination was not just a moment of change. It was a crucial catalyst in the unfolding story of the universe, shaping the landscape we observe today. The transformation of the universe from a hot, dense state to the cooler, expanding cosmos we observe today is rooted in a fascinating journey that began shortly after the Big Bang. Initially, the universe was an incredibly compact environment, filled with energy and radiation. This primordial state couldn't even form distinct particles. Everything was a chaotic mix of high-energy conditions. As the universe began to expand, a fundamental change occurred. Imagine the rapid inflation of a balloon as it's blown up. At this early phase, just moments after the Big Bang, space itself expanded dramatically. This expansion caused the temperatures to drop, allowing for the formation of basic particles like protons, neutrons, and electrons, akin to tiny building blocks. As the universe continued to cool, these particles combined to form light atoms, primarily hydrogen and helium. This era is often referred to as the recombination period. When the temperature became low enough for electrons to be captured by nuclei, the universe transitioned into a more structured entity. This significant event allowed photons, or light particles, to travel freely through space, creating what we recognize today as the cosmic microwave background radiation, the faint afterglow of that hot early universe. Over billions of years, as the universe expanded further, gravitational forces began to take charge. Regions of gas and dark matter started to clump together, giving rise to stars and galaxies. This ongoing expansion continues to this day as galaxies drift further apart from one another, marking the evolution of a cooler and increasingly complex cosmos. Thus, what began as an intense and hot soup of energy transformed through gradual cooling and expansion into the vast universe filled with stars, planets, and galaxies we explore and study today. Galaxies are vast collections of stars, dust, gas, and dark matter, all bound together by gravity. The formation of galaxies begins in the early universe shortly after the Big Bang. Imagine the universe as a fresh canvas with tiny fluctuations in density occurring throughout the expanding material. Over eons, these fluctuations allow regions with slightly more matter to attract surrounding materials, igniting a cosmic process that leads to the coalescence of gas and dust into the first proto-galaxies. As these early structures gather mass, they evolve. They can collide and merge with others, leading to the dynamic formation of larger galaxies. Throughout this process, stellar winds and the gravitational influence of these young galaxies cause gas clouds to compress, triggering the birth of new stars. This cycle of star formation, aging, and death intricately shapes the galaxy's structures and sizes. Galaxies can be broadly categorized into several types based on their shapes and characteristics. The most common are spiral galaxies, identifiable by their swirling arms that extend from a central bulge. These arms often house star-forming regions filled with young, bright stars. In contrast, elliptical galaxies resemble elongated spheres, exhibiting a smooth, featureless appearance. They typically contain older, cooler stars and less interstellar gas, meaning lower rates of new star formation. Then, there are irregular galaxies, which defy any simple classification owing to their chaotic shapes. They often contain a mix of young and old stars and can result from gravitational interactions or collisions with other galaxies, leading to their unpredictable appearances. Finally, there are lenticular galaxies, which present characteristics of both spiral and elliptical galaxies. Similar to an elliptical structure yet possessing a disk, they often feature a bulge in the center but lack pronounced spiral arms. Each galaxy type tells a story of the cosmos, revealing the complex interactions of gravity, light, and time that shape them. Their study not only enhances our understanding of the universe's history, but also provides insights into the ongoing processes that govern cosmic evolution. Dark matter is an elusive substance that makes up a significant portion of the universe's total mass, yet it does not emit or absorb light, making it invisible and detectable only through its gravitational effects. Think of it as an unseen framework that guides the formation and behavior of galaxies. Without dark matter, the universe as we understand it would look vastly different. As galaxies form, they gather mass from clouds of gas and dust. Gravity pulls this matter together, but for galaxies to develop their spiral shapes and maintain their structure, they require much more mass than what we can see. This is where dark matter becomes crucial. It exists as a vast halo, surrounding galaxies and extending well beyond their visible edges. This halo contributes the gravitational pull necessary to hold galaxies together and to ensure they rotate at the speeds observed, preventing them from flying apart. When we observe clusters of galaxies, we notice that the visible mass does not account for the gravitational effects at play. The outer regions of galaxies are rotating faster than they should if only the visible matter were present. The additional gravitational pull supplied by dark matter accounts for this discrepancy, indicating that there is much more mass influencing these astronomical structures than we can detect with our instruments. Moreover, dark matter plays a vital role in the larger-scale structure of the universe. It acts as a scaffold that influences the distribution of galaxies and clusters, shaping the cosmic web we see today. Areas of higher density where dark matter collects attract ordinary matter, leading to the formation of galaxies. Thus, without dark matter, galaxies wouldn't just be different. Many of them might not exist at all. Thus, without dark matter, galaxies wouldn't just be different. Many of them might not exist at all. Its presence is fundamental to understanding how galaxies evolve, interact, and remain stable through cosmic time. Supermassive black holes sit at the heart of most large galaxies, functioning as colossal gravitational anchors within their cosmic neighborhoods. These behemoths can contain the mass equivalent to millions or even billions of suns, and their presence plays a crucial role in the evolution of galaxies. Imagine a massive sphere of darkness surrounded by swirling clouds of stars and gas. This black hole exerts an immense gravitational pull, which helps to regulate the motion of surrounding stars. Their influence stretches outwards, shaping the structure of the galaxy itself. As stars orbit around these black holes, they experience changes in speed and direction, contributing to the overall dynamic behavior of the galaxy. Furthermore, supermassive black holes are linked to the activity known as active galactic nuclei. When matter spirals into a black hole, it heats up and emits powerful streams of energy, making the galaxy's core shine exceptionally bright compared to the outer regions. This brilliance can be observed across vast distances in the universe, serving as a beacon that helps astronomers study the formation and growth of galaxies over billions of years. Another key aspect of supermassive black holes is their role in galaxy evolution. The energy released during the process of accretion, when material is drawn into the black hole, can affect gas dynamics in the galaxy. It might influence star formation rates, either by heating surrounding gas, preventing it from collapsing into new stars, or by generating powerful outflows that redistribute material throughout the galaxy. Thus, the interplay between supermassive black holes and their host galaxies is intricate, casting a long shadow over their developmental pathways. Understanding supermassive black holes sheds light on fundamental questions about the cosmos, such as how galaxies form and evolve over time. It reveals the interconnectedness of structures across the universe, making them a focal point of modern astrophysical research. These enigmatic giants not only govern the behavior of their galactic hosts, but also unlock many mysteries about the history and fate of the universe itself. Galactic collisions are not just spectacular cosmic events, they play a crucial role in shaping the universe's large-scale structure. When two galaxies come close enough, their gravitational forces interact, pulling at each other with tremendous strength. This interaction can lead to various outcomes, from minor distortions to full-blown mergers, where the two galaxies combine into a single, larger entity. As galaxies collide, their stars rarely crash into one another due to the vast distances between them. However, the gas and dust within these galaxies can collide, triggering a burst of star formation. This is akin to shaking a box full of marbles. The movement results in new clusters forming in unexpected places. As new stars ignite in these star-forming regions, they emit light that can illuminate the surrounding interstellar environment, influencing the formation of new structures. The merging galaxies can also initiate a profound transformation of their overall shape and structure. Each galaxy's gravitational field alters, causing previously distinct features to dissipate and new structures to emerge. This blending can lead to the development of elongated arms or the creation of elliptical galaxies as the features of the colliding galaxies combine and fade. On a grander scale, these collisions impact the distribution of galaxies in the universe. Over billions of years, as galaxies collide and merge, they feed into the cosmic web of dark matter, the unseen framework that underlies the visible universe. This process can lead to the formation of galaxy clusters, where dense concentrations of galaxies coexist within the vast voids of space. The aftermath of such collisions also affects the orientation and movement of galaxies. When they merge, the resulting gravitational landscape influences how other galaxies move and interact within the vicinity, creating a dynamic, interconnected universe. Ultimately, the collisions between galaxies contribute to the ongoing evolution of the cosmos, demonstrating that even cataclysmic events can serve as catalysts for growth and change within this vast astronomical tapestry. Spiral arms are a defining feature of spiral galaxies, serving as both functional and structural elements in their evolution. Imagine a galaxy as a giant rotating disk of stars, gas, and dust. The spiral arms act like highways within this cosmic expanse, channels through which material can flow, converse, and birth new stars. These dynamic arms form due to gravitational interactions, where density waves move through the galaxy, causing regions of higher density. As stars and gas clump together within these arms, they trigger bursts of star formation, creating young, vibrant stars that illuminate the arms with brightness. This process continuously enhances the galaxy's beauty and complexity. Over time, as stars age and die, their remnants are recycled back into the galactic ecosystem, fueling subsequent generations of stars. Spiral arms also play a crucial role in shaping the overall structure of the galaxy itself. They help maintain the galaxy's rotation, influencing how the stars and gas interact, drift, and coalesce over billions of years. Interestingly, these arms can be seen as signs of the galaxy's ongoing evolution. Their presence signifies a galaxy that is vibrant and has an active star formation process. Spiral arms are not just attractive features, they are fundamental to the life cycle of spiral galaxies. They facilitate ongoing stellar creation, influence galactic dynamics, and provide insight into the evolutionary history of these magnificent celestial structures. Through a continuous dance of gravity, motion, and time, spiral galaxies grow and transform, with their spiral arms leading the way. Star formation begins in vast clouds of gas and dust, predominantly composed of hydrogen. Picture these clouds as dense, cold regions of space where particles exist in a delicate balance. Over time, certain areas within these clouds become denser due to gravitational forces. As more matter congregates, the pull of gravity intensifies, causing the gas and dust to clump together. As these clumps accumulate additional material, they contract and heat up, generating pressure at their core. Imagine squeezing a ball of soft clay. The more you compress it, the warmer it becomes. This process continues until the core reaches incredibly high temperatures, fueling nuclear reactions in a remarkable transformation. Once the temperature and pressure reach critical levels, hydrogen nuclei begin to fuse into helium, a process that releases immense energy. This energy creates radiation pressure, which is the outward force that balances the inward pull of gravity. When these forces stabilize, a new star is born. Surrounding materials can form a spinning disk, which may give rise to planets and other celestial bodies. Thus, from the interplay of gravity, pressure, and energy, simple clouds of gas evolve into magnificent stars, illuminating the cosmos and igniting further development in their surrounding environments. Nuclear fusion is the powerful process that fuels stars, transforming them from massive clouds of gas into brilliant, shining spheres. At its core, fusion occurs under the extreme conditions found in a star's core, where temperatures soar to millions of degrees and pressures are immense due to the star's own gravitational pull. Under these conditions, light atomic nuclei, primarily hydrogen, collide with enough force to overcome their natural repulsion. When they merge, they form heavier elements while releasing enormous amounts of energy in the process. To picture this, think of it as a series of delicate dances between particles. In the heart of a star, hydrogen nuclei come together to create helium, the second lightest element. This fusion of hydrogen into helium is the primary reaction in stars like our Sun, providing the energy that radiates outward and supports the star against gravitational collapse. The process doesn't stop there. As a star ages and exhausts its hydrogen, it can fuse helium into heavier elements like carbon and oxygen, and eventually, even heavier nuclei can be created during the later stages of a star's life cycle, producing elements like neon, magnesium, and iron. During the life and subsequent death of these stars, the newly formed elements are scattered across the universe, enriching the interstellar medium. This cycle of fusion and explosion not only powers the stars, but also contributes to the creation of the diverse array of elements found on planets and in living things. Ultimately, fusion is not just a source of energy. It's the fundamental process that shapes the cosmos and provides the building blocks for everything we know. The life cycle of a star like our Sun is a fascinating journey that spans billions of years, beginning with its birth in a massive cloud of gas and dust. This cloud, composed primarily of hydrogen, begins to collapse under its own gravity. As the material clumps together, it heats up and forms a protostar, a dense ball at the core surrounded by a disk of gas and dust. Over time, this core continues to accumulate mass and temperature, eventually reaching conditions that ignite nuclear fusion. When fusion starts, hydrogen atoms combine to form helium, releasing tremendous energy in the process. This marks the birth of a main sequence star, a stable phase where the Sun will spend the majority of its life, approximately 10 billion years. During this time, the energy produced in its core counteracts the force of gravity, allowing the star to maintain a stable size and temperature. Our Sun, shining brightly and consistently, is currently in this main sequence stage. As the hydrogen fuel begins to deplete, the balance within the star starts to shift. The core contracts, causing it to heat up, while the outer layers expand and cool, transforming the Sun into a red giant. This phase initiates a new round of fusion. At this point, helium begins to fuse into heavier elements. The outer atmosphere of the Sun swells and could eventually engulf nearby planets. As the Sun exhausts its helium fuel, it will undergo further phases of instability. Ultimately, it will shed its outer layers, creating a beautiful shell of gas known as a planetary nebula. What remains at the core is a hot, dense remnant called a white dwarf, which no longer undergoes fusion reactions. This white dwarf will gradually cool and fade over billions of years. In the end, the Sun's journey showcases the life cycle of stellar evolution, marked by distinct stages over immense timescales. From a glowing ball of gas to a luminous celestial spectre, the transformation is a reminder of the dynamic processes governing our universe. Massive stars have a dramatic life cycle that culminates in an explosive finale. Throughout their existence, they undergo a series of nuclear fusion processes, fusing lighter elements into heavier ones, sustaining their energy output and balance against gravitational collapse. As a massive star exhausts its nuclear fuel, it transitions through various stages, creating elements like carbon, oxygen, and even iron in its core. Eventually, when iron begins to accumulate, a critical change occurs. Iron does not release energy when it fuses, instead, it absorbs it. This marks the point where the star can no longer support itself against the immense gravitational forces pulling inward. With no energy-producing reactions to counteract this force, the core succumbs to gravity, collapsing rapidly while the outer layers of the star remain intact for a brief moment. In this cataclysmic end, the core's collapse leads to an extraordinary rebound effect. It's akin to a bounce back from a deep dive. The outer layers, unable to maintain their support, implode towards the core and are then violently expelled outward. This colossal explosion is what we know as a supernova. In that moment, a supernova releases a brilliant burst of light and energy, outshining entire galaxies for a period. It disperses the star's materials into space, enriching the interstellar medium with the elements forged during its lifetime. What follows is equally fascinating. The remnants of the core, depending on its mass, can become either a neutron star or, if particularly massive, collapse into a black hole. The death of a massive star is a grand recycling event, seeding the cosmos with the building blocks for future stars and planets, driving the very evolution of the universe itself. When massive stars reach the end of their life cycles, they undergo a dramatic transformation that can lead to the birth of either neutron stars or black holes. This transformation begins once a massive star has exhausted the nuclear fuel in its core. As the core collapses under its own gravity, it becomes increasingly compact. If the remaining mass of the core is not too extreme, it compresses to the point where protons and electrons combine to form neutrons, resulting in a neutron star. Imagine an object with the mass of a sun, but shrunk down to the size of a city. The density here is astronomical, as a small spoonful of neutron star material would weigh about the same as an entire mountain on Earth. This incredibly dense condition creates a powerful gravitational field. Neutron stars often spin rapidly and emit beams of radiation, leading to the mesmerizing phenomenon known as pulsars. On the other hand, if the core's mass exceeds a certain limit, often described as a threshold that is more than just a few times the mass of the Sun, the gravitational collapse continues unabated. In this case, no known forces can counteract the pull of gravity, and the star collapses beyond the neutron star stage into a black hole. Visualize it as a region where gravity is so strong that nothing, not even light, can escape it. The boundary surrounding this region is called the event horizon, where all paths lead inward. The explosive deaths of these massive stars, particularly through a supernova, often scatter their outer layers across space, leaving behind these remnants, either neutron stars or black holes, which profoundly influence their surroundings. The evolution of these entities illuminates the intricate dance of nature's forces at work in the universe, revealing how the end of one existence can seed the beginnings of others. The formation of our solar system is a fascinating story that begins with a massive cloud of gas and dust known as a solar nebula. Imagine a colossal nebula composed of elements that were forged in previous generations of stars. This cloud became unstable, possibly due to shock waves from nearby supernova explosions. Slowly, it began to contract under its own gravity, causing the material at its center to accumulate and heat up, forming what we recognize as the Sun. As the Sun ignited, it released energy that pushed much of the remaining gas outward, creating a spinning disk of material surrounding it. Within this spinning disk, particles collided and stuck together, gradually forming larger and larger clumps, a process known as accretion. These clumps eventually became the planets, moons, comets, and asteroids we see today. The inner section of the disk, where it's hotter, allowed the formation of rocky planets like Earth and Mars, while the outer regions, being cooler, birthed gas giants like Jupiter and Saturn. Current theories about this process are grounded in extensive observations and simulations. One central idea is called the solar nebula theory, which details how gravity and the conservation of angular momentum led to the systematic formation of our solar system's various bodies. This theory explains not only the arrangement of planets, but also their compositions and orbits. Another theory gaining traction is the concept of the Nice model. Named after the city in France where key research took place, this theory suggests that the early solar system underwent significant rearrangement. Specifically, after the planets formed, gravitational interactions between them, particularly the large gas giants, led to dramatic changes in their orbits. This could explain the unusual orbits of some distant objects known as trans-Neptunian objects and the steep incline of the solar system's outer region. Overall, while we have a solid understanding of the general processes involved in the formation of our solar system, researchers continue to study its intricate details, piecing together the cosmic puzzle that created our home amidst the vastness of the universe. Earth stands out in our solar system as a uniquely hospitable planet for life, and several key factors contribute to this distinction. First and foremost is its position in what scientists refer to as the habitable zone, an area around the Sun where conditions are just right for liquid water to exist. Water is essential for life as we know it, acting as a solvent for biochemical reactions and playing a crucial role in regulating temperatures. Furthermore, Earth's atmosphere is a critical component of its ability to support life. It is composed mostly of nitrogen and oxygen, creating a stable environment that not only protects living organisms from harmful radiation, but also helps maintain a comfortable temperature range. This protective layer shields the planet from the sun's intense rays and allows for weather patterns that distribute heat and moisture. Another important characteristic is Earth's geological activity. The presence of tectonic plates contributes to a dynamic environment that recycles nutrients and shapes diverse habitats. This geological process not only creates varying landscapes, from mountains to valleys, but also plays a pivotal role in the carbon cycle, which helps regulate the planet's climate over long periods. Additionally, Earth's magnetic field serves as a shield against solar winds, which are streams of charged particles emitted by the sun. This magnetic barrier protects the atmosphere from being stripped away, ensuring that vital gases remain and are not lost to space. Life on Earth has also benefited from its relatively stable climate and the planet's abundance of diverse ecosystems. From lush rainforests to arid deserts, these varying environments provide numerous niches where life can thrive. In sum, Earth's ideal location, protective atmosphere, geological activity, strong magnetic field, and diverse ecosystems all work in unison to create a planet that is uniquely suited for the complex and varied forms of life that call it home. Scientists explore the possibility of life on Mars and other planets through a multifaceted approach that combines technological ingenuity and methodical exploration. They begin by focusing on environments where life as we know it could exist, specifically looking for the presence of water, as it is essential for life. On Mars, missions have detected evidence of past water flows, such as riverbeds and minerals that form in water, suggesting that the planet once had favorable conditions for life. Robotic missions play a pivotal role in this exploration. Rovers, equipped with a variety of scientific instruments, traverse the surface of planets, analyzing soil and rock samples to identify organic compounds, basic building blocks of life. These rovers are capable of conducting experiments in situ, meaning they analyze their surroundings without needing to return samples to Earth. This allows scientists to gather immediate data about the planet's chemistry and potential biological activity. Moreover, telescopes and space probes extend our reach to distant worlds. They analyze atmospheres and surface conditions by detecting gas signatures, such as methane, which may indicate biological processes. For instance, the presence of specific gas combinations could hint at the potential for life, requiring further investigation. Laboratory simulations also provide critical insight. Researchers recreate planetary environments on Earth to study how life might adapt or survive under extreme conditions, from the frigid temperatures of outer planets to the high radiation levels found on Mars. These experiments help scientists understand the limits of life and how it may exist under conditions very different from those on Earth. Collaborative international efforts enhance these endeavors. Space agencies share findings, technology, and expertise, fueling a collective understanding of where to look for life and how to interpret the data gathered. By piecing together geological history, atmospheric analysis, and potential biosignatures, scientists continue to unravel the mysteries of life beyond our planet, always searching for the tantalizing possibility that we are not alone in the cosmos. The outer planets, often referred to as gas giants, hold numerous mysteries and captivating traits that intrigue scientists and space enthusiasts alike. Unlike the rocky inner planets, these massive worlds are composed mainly of gases and possess different characteristics that set them apart. Jupiter, the largest of the outer planets, boasts a swirling atmosphere filled with storms, including the Great Red Spot, a gigantic storm larger than Earth that has raged for centuries. Its vast magnetic field and dozens of moons, including volcanic Io and icy Europa, suggest a dynamic system rich with geological activity and potential for life in the subsurface ocean believed to exist beneath Europa's icy crust. Saturn is renowned for its stunning rings, made mostly of ice particles and rocky debris. These rings, while beautiful, raise questions about their formation and lifespan. Saturn's numerous moons, such as Titan, capture attention as well. Titan features a thick atmosphere and lakes of liquid methane, offering a glimpse into an alien environment that is intriguingly similar, yet starkly different from Earth. Uranus presents a unique tilt, rotating on its side relative to its orbit, creating extreme seasonal variations. Its deep blue color is due to the presence of methane in the atmosphere, which absorbs red light. The planet and its moons, like Miranda with its strange geological features, remain less understood and suggest a violent past, possibly involving collisions with other celestial bodies. Neptune, the farthest from the Sun, showcases some of the strongest winds in the solar system, reaching speeds that defy forecasts based on its distance from the Sun. Its vivid blue hue, also influenced by methane, hints at complex atmospheric processes, while its dynamic weather patterns and dark storms present opportunities for further research. Together, the mysteries of these outer planets invite ongoing exploration. They challenge our understanding of planet formation and evolution, pushing the boundaries of our knowledge about the solar system and the potential for diverse environments throughout the universe. Each of these planets, with its unique characteristics and enigmatic phenomena, contributes to an intricate picture of our cosmic neighborhood, urging scientists to unravel the secrets hidden within their thick atmospheres and icy moons. Studying asteroids and comets offers a unique window into the early history of our solar system. These objects are remnants from its formation, often described as time capsules carrying clues about the conditions that existed billions of years ago. By examining their composition, scientists can infer the building blocks of the Earth and other planets. Asteroids, primarily found in the belt between Mars and Jupiter, are made mostly of rock and metal. Many of these objects are believed to be leftovers from the planet formation process, revealing what materials were available at that time. When scientists analyze the minerals and elements within these asteroids, they gain insights into the temperature and pressure conditions present during the early solar system. For instance, the presence of certain types of minerals indicates how far from the Sun these bodies formed, as temperature dramatically affects the materials that can condense and solidify. Comets, on the other hand, originate from the colder outer regions of the solar system. Composed largely of ice, dust, and rocky materials, comets are often referred to as dirty snowballs. When a comet approaches the Sun, its ice vaporizes, releasing gas and dust that form a glowing coma and often a tail. By studying these phenomena, scientists learn about the primordial materials that contributed to the formation of planets. The organic compounds found within comets, including amino acids, hint that the basic ingredients for life may have been delivered to Earth through these ancient travelers. Moreover, the impact history of asteroids and comets tells us about the dynamic processes that influence the evolution of the solar system. Collisions have played a significant role in shaping the surfaces of planets and moons, leading to craters and generating significant geological changes. By understanding the frequency and effects of these impacts, scientists can better assess how they might have contributed to the conditions necessary for life on Earth. Asteroids and comets hold the key to piecing together the intricate puzzle of our solar system's origins, evolution, and the fundamental processes that may also be applicable to other planetary systems in the universe. Each mission that visits these bodies provides further details, enhancing our comprehension and appreciation of the cosmos we inhabit. Telescopes and observatories have revolutionized our comprehension of the universe by allowing us to see beyond the naked eye's limitations. Imagine looking up at the night sky and only being able to witness a handful of stars. Now, picture the marvel of turning a powerful telescope toward those same skies. Suddenly, thousands of stars, distant galaxies, and even the intricate details of planetary systems come into view. This is the magic of optics, gathering light from celestial bodies and amplifying it, giving us a clearer picture of what lies beyond our world. As technology has progressed, so too have our telescopes. Early instruments relied solely on lenses to capture light. Today, we utilize a combination of lenses and mirrors, creating more powerful telescopes that can detect not just visible light, but also infrared and ultraviolet rays. This allows astronomers to study phenomena that are not visible to the human eye. For example, using infrared telescopes, we can peer through thick clouds of dust in space to observe star formation occurring within. This enhanced vision offers an unprecedented insight into the processes that shape the cosmos. Observatories also play a crucial role in our explorations. Ground-based observatories are strategically placed in high-altitude locations where the atmosphere is thinner, allowing for clearer observations. Meanwhile, space-based observatories, like the famous Hubble Space Telescope, venture beyond Earth's atmospheric interference entirely, providing crystal-clear images of distant galaxies and nebulae. With every photograph taken from these vantage points, we uncover new details, like the existence of exoplanets or the discovery of previously unknown celestial formations. The data collected from telescopes and observatories doesn't just increase our knowledge of what exists. It fundamentally alters our understanding of the universe's structure and history. For instance, observations of distant galaxies have shown us that the universe is expanding, leading to the remarkable conclusion that our cosmos has its origins in the Big Bang, a monumental event that occurred billions of years ago. Thus, telescopes have not only enhanced our ability to observe, but have also provided insights that lead to profound questions about the nature of existence, the potential for life beyond Earth, and the overarching mechanics of the universe itself. Through constant innovation, from adaptive optics that correct atmospheric distortions to array telescopes that synchronize multiple instruments, our exploration gears towards ever deeper realms of space. Each advancement in telescope technology uncovers more mysteries, connecting the ancient quest to understand the skies with the modern scientific pursuit of knowledge. Observatories are not mere buildings. They are gateways that bridge our world with the universe, transforming our perceptions of reality and inviting us to ponder our place within the cosmos. Spacecraft missions like Voyager and Hubble have revolutionized our understanding of the universe through their groundbreaking discoveries. The Voyager missions, launched in the late 1970s, were the first human-made objects to travel beyond our solar system. As they flew past the gas giants, Voyager provided us with stunning images and data about Jupiter and Saturn, including their intricate ring systems and dozens of previously unknown moons. This wealth of information reshaped our knowledge of planetary formation and evolution, showing us that these distant worlds are complex and dynamic. Hubble Space Telescope, launched a decade later, opened up the universe to us in unprecedented ways. Positioning itself high above Earth's atmosphere, Hubble avoided much of the distortion caused by atmospheric interference. It delivered breathtaking images of distant galaxies, nebulas, and star clusters, revealing the deep structures of the universe. One of Hubble's most significant contributions was its role in determining the rate of expansion of the universe, leading to the discovery of dark energy, a mysterious force driving that expansion and suggesting the universe is not static but is instead ever-growing. Both spacecraft have fundamentally changed our perspective. Voyager's journey has provided insights into the outer solar system and the interstellar medium, while Hubble has expanded our view into the depths of space. Together, they form a bridge between the near and the far, blending planetary science and cosmology, which deepens our understanding of our own place in the cosmos. Each discovery they made ignited curiosity, leading future generations of scientists and astronomers to explore unanswered questions about the universe. Their legacies continue to inspire ongoing investigations, illustrating how much we have yet to learn about the vast expanses beyond our planet. Modern techniques for detecting gravitational waves have revolutionized our understanding of the universe, providing a new way to observe celestial events that were previously invisible to traditional telescopes. Gravitational waves are ripples in the fabric of space-time generated by some of the universe's most cataclysmic events, such as the merger of black holes or neutron stars. Imagine the universe as a vast ocean. These waves are like stones thrown into the water, sending ripples across the surface. When a massive event occurs, it not only releases energy in the form of light or radiation, but also disturbs the surrounding space-time, creating waves that travel across the cosmos. Advanced detectors, such as those used in the Laser Interferometer Gravitational Wave Observatory, measure minuscule changes in distance caused by these waves as they pass through Earth. This innovative technology allows scientists to capture data that would otherwise remain unobserved, unlocking a wealth of information about the most extreme environments in the universe. With the ability to detect gravitational waves, researchers can explore phenomena that emit little or no light, revealing insights into the behaviors and characteristics of black holes and neutron stars. This adds a powerful dimension to astrophysics, as we can now investigate the processes behind stellar evolution and the dynamics of cosmic collisions in ways that traditional observations alone could not achieve. Moreover, the observations of gravitational waves complement electromagnetic radiation, light, radio waves, and X-rays, offering a fuller, multifaceted perspective of astronomical events. Each detection deepens our understanding and raises new questions about the nature of gravity, the formation of exotic objects, and the evolution of the universe itself. Thus, gravitational wave detection emerges not just as a tool, but as a groundbreaking approach that paves the way for expanded exploration and comprehension of our cosmic surroundings. Exploring exoplanets and distant stars presents a fascinating array of challenges that scientists and astronomers are continuously working to overcome. One of the primary difficulties is the sheer vastness of space. Exoplanets are located light-years away, a distance so great that even our fastest spacecraft would take thousands of years to reach the nearest ones. This immense separation means that we must rely on indirect methods to study these distant worlds, instead of visiting them and gathering data firsthand. Another significant challenge is the limitations of our current technology. Telescopes, for example, can reveal a wealth of information about distant stars and planets, but they operate under constraints of light sensitivity and resolution. Detecting the faint light from a distant star, especially when trying to discern the reflective light from an orbiting planet, requires incredibly sophisticated instruments. Even with advanced technologies, the light from exoplanets can be overwhelmed by their parent stars. Thus, scientists need to develop innovative techniques to isolate that light and analyze it. Moreover, the atmosphere of exoplanets, if they exist, poses additional complexities. Understanding their chemical compositions, whether they have suitable conditions for life, or even their surface temperatures, involves interpreting the starlight that passes through their atmospheres. This requires precise spectrographic analysis, an intricate process that allows scientists to identify specific molecules by their unique signatures. The challenge lies not only in detecting these signatures, but also in distinguishing them from other potential interference from space dust and gas. There's also the issue of time. The universe is constantly evolving, and many phenomena happen over timescales that far exceed human lifespans or even technological development cycles. Observatories may only capture fleeting moments of cosmic events, making it difficult to secure complete datasets. Lastly, funding and international collaboration can play crucial roles in the exploration of exoplanets and distant stars. High-quality research and missions often require immense investments and cooperation between nations and space agencies. Political and economic factors can affect the continuity and advancement of ongoing projects, potentially stalling progress on exciting discoveries. These challenges are daunting, yet they drive the quest for knowledge, pushing humanity to develop better tools and adopt creative approaches in exploring the cosmos. Each obstacle presents an opportunity for innovation, highlighting the resilience of our quest to understand the universe beyond our own world. Artificial intelligence is revolutionizing our exploration and understanding of the universe in profound ways. Traditionally, studying celestial phenomena required intense manual labor, analyzing vast amounts of data collected from telescopes or space missions. Now, with the aid of AI, scientists can process and interpret this data much more efficiently. Imagine an astronomical database filled with billions of images and observations collected over decades. AI algorithms can sift through this massive trove of information rapidly, identifying patterns and anomalies that would easily escape human eyes. One of the most exciting applications is in the discovery of exoplanets, which are planets outside our solar system. AI models can examine variations in starlight caused by planets passing in front of their host stars, known as transits. This automation accelerates the detection process, enabling scientists to identify promising candidates for further study, dramatically increasing the rate of discoveries. Moreover, AI is enhancing our understanding of cosmic events. For instance, in the realm of gravitational waves, ripples in spacetime caused by cataclysmic events like the merging of black holes, AI helps in pinpointing the exact moments and locations of these events. This capability allows for timely observations across different wavelengths, unveiling the mysteries of the universe with unprecedented clarity. Machine learning, a subset of AI, is also transforming our ability to model complex systems. By training on existing data, these algorithms can generate simulations that explore a variety of cosmic scenarios, from the behavior of galaxies to the evolution of the universe itself. This provides researchers with valuable insights, guiding hypotheses and informing future studies. Artificial intelligence acts as both a powerful tool and an innovative partner. It expands the horizons of our inquiry, driving human understanding deeper into the vast, complex fabric of the cosmos. As this technology continues to evolve, the frontiers of space science are likely to stretch even further, leading us to discoveries that could change our perspective on existence itself. Dark energy is a mysterious form of energy that makes up much of the universe and is crucial in understanding its expansion. To visualize its impact, think of the universe as being in a balloon. As the balloon inflates, it expands, and dark energy acts like the air filling it, pushing outward and making the balloon grow larger at an increasing pace. After the Big Bang, the universe began to expand, but it was initially influenced by gravity, which tended to slow this expansion. Over time, as galaxies moved apart, something unusual happened around 5 billion years ago. The rate of expansion began to rise instead of slowing down. This is where dark energy enters the picture. It works against gravity, overpowering it to send galaxies racing further apart at an accelerating rate. What dark energy exactly is remains uncertain, but it is thought to have a uniform presence throughout space. Unlike matter, which can clump together under the influence of gravity, dark energy remains evenly distributed, leading to a repulsive effect that pushes galaxies away from each other. Scientists suspect that it could be linked to the energy of empty space itself, a concept known as the cosmological constant, or might represent a dynamic field affecting the universe differently over time. As researchers continue to study this enigmatic force, it raises profound questions about the ultimate fate of the universe. Will galaxies drift so far apart that the night sky becomes dark and silent? The answers may redefine our understanding of space, time, and the very nature of reality itself. Scientists explore the possibility of other dimensions beyond our observable universe by delving into the fascinating realms of theoretical physics and advanced mathematics. Their quest often begins with the fundamental principles of our universe, specifically those defined by theories such as string theory and quantum mechanics. String theory posits that the basic building blocks of reality are not point-like particles, but rather tiny, vibrating strings. These strings can exist in multiple dimensions beyond the familiar three of space and one of time. By employing mathematical frameworks, physicists theorize that additional dimensions might be compactified, meaning they could be incredibly small and tightly curled up, making them difficult to detect directly. Techniques like studying particle collisions in high-energy environments, such as those found in particle accelerators, help probe the energy levels where the effects of these extra dimensions might become evident. Furthermore, scientists investigate the cosmic background radiation, the afterglow of the Big Bang, looking for anomalies that could hint at dimensions beyond our observable universe. The idea is that interactions in these additional dimensions could manifest as slight discrepancies in the radiation's uniformity. Advanced astronomical observations also play a crucial role, particularly in studying cosmic structures and gravitational phenomena. The behavior of galaxies and the distribution of dark matter provide clues that could indicate the influence of hidden dimensions. Ultimately, while these concepts remain highly speculative, the constant interplay of theory, experimentation, and observation provides a means for scientists to inch closer to understanding the possibility of other dimensions and how they might shape our reality. The concept of wormholes and the potential for time travel emerge from the theories of relativity proposed by Albert Einstein. Einstein introduced the notion that space and time are intertwined into a single entity called spacetime. They function as bridges connecting separate points in spacetime. Imagine being able to travel from Earth to a distant star system not by moving through the vast emptiness in between, but instead hopping through a tunnel that links them. These hypothetical structures, although mathematically possible, have yet to be observed in nature. Their existence relies on various exotic conditions, including the presence of negative energy, something we have yet to find in a stable, usable form. When considering time travel, the situation becomes even more complex. Einstein's equations allow for scenarios where time can be manipulated under certain conditions. For example, if one could travel at speeds approaching that of light, or even create a rotating black hole, one might theoretically experience time differently compared to a stationary observer. Such effects, known as time dilation, have already been observed in experiments with high-speed particles and precise clocks on airplanes. However, these theoretical avenues bear numerous complications. For instance, creating a stable wormhole may require technologies and materials beyond our current capabilities, as well as a profound understanding of quantum mechanics, which emphasizes the inherently unpredictable nature of the smallest constituents of matter. While intriguing ideas flourish around wormholes and time travel, the scientific community remains cautious. Current evidence leans on the foundation laid by Einstein's theories, yet tangible proof is elusive, captured only within the realms of theoretical physics. As our understanding of the universe expands, the quest to validate these extraordinary phenomena persists, inviting both scientific inquiry and imagination. Detecting black holes is a fascinating challenge for scientists because they do not emit light. Instead, astronomers rely on indirect evidence to identify their presence. One of the main methods involves observing the effects of a black hole's gravitational force on nearby stars and gas. When a star orbits around an invisible object, that object's mass can be inferred by how fast the star moves and its path through space. This dance of celestial bodies can reveal the presence of a black hole, even when it's completely shrouded in darkness. Another crucial method utilizes the detection of X-rays. If a black hole is actively consuming material from a companion star, the intense gravitational forces compress and heat that material, causing it to emit X-rays. Telescopes that can observe these high-energy emissions, like the Chandra X-ray Observatory, have provided compelling evidence for numerous black holes lurking in our universe. Recent findings have advanced our understanding of black holes significantly. For instance, scientists at the Event Horizon Telescope collaboration managed to capture the first image of a black hole in the galaxy M87. This monumental achievement provided a visual confirmation of their existence and offered insights into their structure, showing a dark shadow surrounded by a bright ring of light composed of superheated gas. Additionally, gravitational waves, ripples in spacetime caused by massive cosmic events like black hole collisions, have opened up a new frontier in astronomy. Gracefully detected by the LIGO and Virgo observatories, these waves provide a fresh way to study aspects of black holes, including their masses and spins, as well as details about how often they merge. The latest research is not just about confirming their existence, but understanding their dynamic nature. Observations suggest that black holes can grow rapidly by devouring matter or merging with other black holes. This growth can influence the formation and evolution of galaxies, making black holes key players in the cosmic landscape. Their behavior, previously thought to be static, is now understood to be much more interconnected with the surrounding galaxy, propelling fascinating discussions about the role of these enigmatic giants in the universe's history. Quasars are incredibly luminous objects powered by supermassive black holes at the centers of distant galaxies. When matter spirals into these black holes, it heats up dramatically, emitting immense amounts of energy that can outshine entire galaxies. Imagine a single beacon of light that casts a glow across billions of light years, outshining all the stars in its host galaxy. These fascinating entities are key to understanding the early universe for several reasons. Quasars formed when the universe was still quite young, often just a few billion years after the Big Bang. Their brightness allows astronomers to study them even from vast distances, providing a glimpse into the conditions that existed during the universe's formative years. By observing quasars, scientists can gather crucial insights about the growth of black holes, the formation of galaxies, and the distribution of matter in the early cosmos. They serve as cosmic time capsules, revealing not just their own properties, but also how the universe evolved over time. Studying quasars helps researchers understand large-scale structures, the rate of star formation, and even the influence of dark matter, highlighting their significance in piecing together the narrative of our universe's ancient history. The exploration of extremophiles, remarkable organisms that thrive in Earth's most inhospitable environments, offers profound insights into the search for life beyond our planet. These resilient life forms can survive extreme temperatures, intense radiation, crushing pressures, and highly acidic or alkaline conditions. By studying extremophiles, scientists uncover the various adaptations that enable life to persist where it seems impossible. For instance, some extremophiles can endure temperatures that would melt conventional forms of life, indicating that organisms might exist in the frigid or scalding conditions on other celestial bodies, like the icy moons of Jupiter or the scorching surface of Venus. Understanding how these extremophiles manage cellular processes under such extreme conditions expands our definition of where life might exist and how it could function. Moreover, insights gathered from extremophiles contribute to astrobiology, the field that examines the potential for life in various environments across the universe. By modeling and simulating how these organisms behave in harsh conditions, researchers can apply similar principles when investigating places like Mars, where past water activity suggests the possibility of microbial life. Additionally, extremophiles have unique biochemical pathways that suggest alternate methods of metabolism, pointing to potential life forms that are fundamentally different from those we know. These discoveries encourage scientists to broaden their search criteria and consider life forms that may rely on different biochemistries, leading to more comprehensive exploratory missions. Ultimately, extremophiles act as a powerful reminder that life's resilience knows no bounds on our own planet. Consequently, their study fuels both optimism and curiosity in the quest to find whether life exists in the unfathomable expanses of the universe. Each discovery pushes the frontiers of our understanding, guiding us closer to the possibility of discovering life beyond Earth. When we gaze into the vast expanse of space, we find a captivating array of distant worlds called exoplanets, planets located outside our solar system. Among the thousands discovered so far, several stand out as particularly promising candidates for supporting life. One of the primary criteria for livability is a location within what scientists term the habitable zone, which is the region around a star where conditions might be just right for liquid water to exist on a planet's surface. Water is essential because it acts as a solvent for life as we know it. A notable example is Proxima Centauri b, a planet orbiting the closest star to our own. It resides within its star's habitable zone and is comparable in size to Earth. This intriguing world offers the potential for liquid water, but challenges such as stellar radiation from its active star raise questions about its atmospheric conditions. Another intriguing candidate is TRAPPIST-1e, part of a system with multiple Earth-sized planets. This planet is located within the habitable zone of a cooler star, which allows it to maintain conditions that could sustain liquid water. The nearby presence of other planets in the same system might provide insights into the evolution of life in diverse environments. Then there's Kepler-180f, the first Earth-sized planet confirmed to be in the habitable zone of a star similar to our Sun. Its location and size suggest that it could possess conditions where life could emerge. Researchers are keenly interested in studying this planet further to understand its atmosphere and surface conditions. Lastly, there's LHS 1140b, which orbits a smaller star. This exoplanet sits comfortably in its star's habitable zone and could provide scientists with the opportunity to analyze its atmosphere for signs of life through future observations. As we continue to refine our search and develop new technologies, looking for biomarkers, substances that could indicate the presence of life on these worlds will be crucial. Each of these exoplanets brings with it the tantalizing possibility of unraveling the age-old question: are we alone in the universe? The search for extraterrestrial intelligence, often referred to as SETI, employs a variety of advanced technologies aimed at detecting signals from civilizations beyond Earth. One of the primary tools in this search is the radio telescope. These large instruments are designed to pick up radio waves emitted from space, much like a giant ear listening for subtle sounds in the cosmic noise. They can scan vast areas of the sky and analyze signals across a broad range of frequencies. In addition to radio telescopes, SETI utilizes powerful computer algorithms and signal processing techniques. These technologies allow scientists to sift through immense amounts of data collected from space, filtering out background noise and identifying anomalies that may indicate artificial signals. This process is akin to searching for a needle in a haystack, with computers helping researchers to rapidly evaluate signals that merit closer examination. Optical telescopes are also part of the SETI toolkit as they search for laser emissions from other civilizations. These lasers, if they exist, could serve as beacons, pulsating in specific patterns that distinguish them from natural celestial phenomena. Sophisticated instruments equipped with high-sensitivity detectors can capture these faint glimmers of light, computing power through projects like SETI Home. This crowdsourced approach allows everyday individuals to aid in the analysis of data, amplifying efforts with collective resources. As technology continues to advance, so too does our ability to listen closely to the cosmos and unravel the mysteries surrounding the possibility of intelligent life beyond our planet. The discovery of exoplanets, or planets orbiting stars outside our own solar system, has dramatically reshaped our perspective on the potential for life beyond Earth. For a long time, scientists speculated whether other worlds might exist, but the ability to confirm their existence has shifted that speculation into a realm of possibility. With thousands of exoplanets now identified, astronomers categorize these worlds into diverse types, some of which lie within a star's habitable zone. This zone is an orbital region where conditions may allow liquid water to persist, a key ingredient for life as we know it. Imagine the vast array of environments these planets could present, ranging from rocky Earth-like planets to gas giants and even super-Earths with heavier atmospheres. Each discovery reinforces the idea that our solar system is just one of many vibrant systems in the galaxy. Furthermore, these findings invite questions about the building blocks of life. Many exoplanets demonstrate characteristics, such as atmosphere composition, that suggest they could harbor the necessary conditions for life. For instance, the detection of carbon dioxide, methane, or even water vapor hints at chemistry that could support biological processes similar to those on Earth. Moreover, as telescopes improve, scientists are developing the capability to analyze the atmospheres of these distant worlds more effectively. By studying how light from a star filters through a planet's atmosphere, researchers can infer the presence of key molecules that might signify biological activity. As we gather more data, a clearer picture emerges, illuminating a universe that could be teeming with potential habitats. Ultimately, the ongoing discoveries of exoplanets shift our understanding from seeing Earth as an isolated oasis to viewing it as one of many potential homes in a vast cosmic neighborhood. This realization fuels the hope that perhaps life exists elsewhere, challenging us to expand our search beyond our planet. The universe is becoming a less lonely place as each new exoplanet discovery invites humanity to consider its role in this grand, expansive cosmos. The discovery of alien life raises profound ethical and philosophical questions that extend beyond the realm of science. Consider first the potential impact on our understanding of humanity's place in the universe. If we find that we are not alone, it may challenge our beliefs about uniqueness and significance. Humanity has often viewed itself as the pinnacle of evolution on Earth, so encountering another form of life could provoke a reassessment of what it means to be human. Moreover, the nature of the life we discover is equally important. If we encounter microbial life, like organisms that could exist on Mars or under the icy crust of Europa, it may lead to debates about protecting these fragile ecosystems. There would be ethical imperatives to ensure that our exploration does not harm their environments. The essence of stewardship comes into play. How do we responsibly manage our actions when the stakes could involve unknown forms of life? Should we discover intelligent extraterrestrial beings, the ethical considerations would multiply exponentially. Questions around communication arise. How do we approach a conversation with a species whose thoughts, culture, and values could be entirely foreign to us? There is also the significant concern of power dynamics. Would humanity attempt to dominate, exploit, or militarize that relationship? The moral obligation to treat other sentient beings with respect, to consider their rights and agency, becomes paramount. Furthermore, the philosophical implications could lead to a re-evaluation of existing belief systems. Discovering alien life could prompt discussions about the nature of existence, the criteria for consciousness and intelligence, and our obligations to other forms of life, however they exist. Theories of ethics may evolve to include non-human entities, expanding the framework through which we view morality. Ultimately, the implications of discovering alien life would not only alter the trajectory of science, but would also demand a collective introspection on our values as a species. It calls for an integrative approach from scientists, ethicists, philosophers, and policymakers to navigate this new frontier with wisdom and foresight. The questions may be daunting, but they offer an incredible opportunity to deepen our understanding of life, both our own and that which might lie beyond the stars. Measuring distances in the vast expanse of the universe is a challenge that scientists have tackled using several innovative techniques. One of the fundamental methods involves triangulation, a system that relies on observing the same object from two different points to create a triangle. By knowing the distance between the observation points on Earth, scientists can use simple geometry to calculate how far away the object is. For stars within our own galaxy, astronomers often employ a technique called parallax. This approach involves taking two observations of a star at different times of the year when Earth is at opposite ends of its orbit around the Sun. By measuring how much the star appears to shift against the background of more distant stars, scientists can calculate its distance based on the angle of this apparent movement. This method works well for stars that are relatively close, but as the distances increase, the shifts become minute and harder to detect. To measure even longer distances, particularly those of galaxies, astronomers utilize something known as standard candles. A standard candle is an object of known brightness, such as certain types of exploding stars called supernovae. By comparing the known brightness of these events with how dim they appear from Earth, scientists can determine how far away they are. This method relies on the understanding that light spreads out as it travels, making distant objects seem fainter. In the most distant reaches of the universe, the concept of redshift comes into play. As the universe expands, light from distant galaxies shifts toward the red end of the spectrum. By measuring this redshift, scientists can deduce both the distance to the galaxy and how quickly it is moving away from us. This interplay between distance and velocity gives astronomers critical insights into the nature of the universe itself. Through these various methods, scientists have built a comprehensive distance ladder that allows them to chart the cosmos with increasing accuracy. Each step in this ladder builds upon the last, helping to unravel the vastness of the universe in a way that makes it more comprehensible. The cosmic microwave background radiation is a pivotal piece of evidence in our understanding of the universe's origins. Imagine the universe just moments after the Big Bang. A hot, dense mass filled with energy and particles was rapidly expanding. As it cooled, approximately 300,000 years after the initial explosion, protons and electrons combined to form hydrogen atoms. This process allowed light to travel freely, marking the moment when the universe became transparent. What we now see as the cosmic microwave background is the afterglow of that early light, stretched into microwave wavelengths as the universe expanded over billions of years. It fills every corner of the cosmos, representing a uniform radiation that is a remnant of that significant phase in the universe's history. The significance of this radiation extends beyond its mere presence. By studying its temperature and tiny fluctuations, scientists can glean insights into the universe's age, composition, and the processes that led to the formation of galaxies. The slight variations in temperature across the cosmic microwave background reveal the seeds of cosmic structure, providing a glimpse into how large-scale formations, such as galaxies and clusters, eventually arose. This radiation serves as a fossil of the early universe, allowing astronomers to paint a coherent picture of how everything began, evolved, and continues to change. It bridges the gap between theory and observation, reinforcing the Big Bang model while also highlighting areas where our understanding may still grow. The cosmic microwave background is not just a remnant, it's a cosmic map guiding our exploration of the universe's deepest mysteries. Determining the age of stars and galaxies is a fascinating process that combines various scientific approaches. Astronomers primarily rely on the concept of stellar evolution, which describes how stars change over time in terms of their size, brightness, and color. By observing a star's current characteristics, scientists can infer its age. To start, astronomers look at a star's position on the Hertzsprung-Russell diagram, a graph that plots stars according to their brightness and surface temperature. Each region on this diagram corresponds to different stages in a star's life cycle. For instance, a star that appears large and bright is likely at a later stage of evolution, whereas a smaller, cooler star may be much younger. By comparing a star's traits to theoretical models of stellar evolution, astronomers can estimate how long it has been shining. In addition to studying individual stars, astronomers also examine star clusters. A star cluster consists of many stars that formed around the same time from the same cloud of gas and dust. By identifying the brightest and oldest stars in a cluster, astronomers can establish a rough age for the entire group. This method is especially useful since these clusters provide a snapshot of different stellar ages. When it comes to galaxies, astronomers consider factors like the age of their oldest stars and the presence of specific elements. Over time, stars create heavier elements through nuclear fusion, contributing to the cosmic environment. A galaxy rich in these elements tends to be older, implying that star formation has occurred over a long period. Observing the light emitted by distant galaxies also reveals how they have evolved through cosmic time, providing clues about when they formed and how they have changed since their inception. Finally, newer techniques involve measuring variations in the cosmic microwave background radiation, the afterglow of the Big Bang. This radiation offers a glance into the early universe and helps researchers estimate the age of the universe itself. By connecting this information with the lifetimes of stars and galaxies, astronomers piece together a timeline that highlights when various cosmic structures came into being. Through these methods, observing stellar properties, studying star clusters, analyzing elemental composition, and evaluating cosmic background radiation, astronomers weave together a narrative of the universe's history, unlocking the secrets of age in stars and galaxies. The Hubble constant plays a crucial role in our comprehension of the universe's expansion. Imagine observing a balloon inflating. As it grows, the points on its surface move away from each other. Similarly, the Hubble constant quantifies how fast galaxies are receding from us as the universe expands. This measurement reveals that distant galaxies are moving away at speeds proportional to their distance from us, a discovery that fundamentally changed our understanding of cosmic dynamics. When astronomers categorize the Hubble constant, they provide a numerical value that indicates the rate of this expansion. A higher value suggests a faster expansion, while a lower value indicates a slower one. This expansion rate also holds implications for the universe's age. By determining how quickly space stretches, scientists can estimate when the universe began, offering insights into its beginnings and evolution. Moreover, the Hubble constant connects with several critical cosmological models and theories, including the Big Bang. It helps astronomers explore whether the expansion is accelerating or decelerating, influenced by factors such as dark energy, which is thought to drive a speeding up in this expansion. The Hubble constant serves as a cornerstone for unraveling the mysteries of the cosmos, guiding our inquiries into the very fabric and fate of the universe. Gravitational lenses are a fascinating cosmic phenomenon where massive objects, such as galaxies or clusters of galaxies, bend the light coming from distant objects behind them. This occurs because, according to Einstein's theory of general relativity, gravity can warp the fabric of space. When light travels near a massive object, its path is altered, much like how a ball would curve around a heavy bowling ball placed on a stretched-out rubber sheet. This bending of light creates a lensing effect, leading observers on Earth to see multiple images of the same distant object, or a distorted, magnified version of it. These effects are not merely visual curiosities, they are powerful tools for astronomers. By studying how the light from distant galaxies is warped, scientists can learn about the intervening matter's distribution, even if that matter is invisible dark matter. Gravitational lenses help confirm theories about the universe's expansion and structure. As light from far-off galaxies reached us with clues about their composition and movements, gravitational lensing allows researchers to glimpse into the history and evolution of the cosmos. By analyzing the exact way light is distorted, astronomers can infer key properties of both the lensing mass and the background objects. This insight aids in answering fundamental questions about the nature of dark matter, the rate of cosmic expansion, and the overall architecture of the universe itself. Thus, gravitational lenses not only reveal breathtaking views of the cosmos, but also unravel complex mysteries of the universe's fabric. The potential endings of our universe have captivated both scientists and philosophers for centuries, leading to several fascinating theories, each rooted in the principles of physics. One predominant scenario is the Big Freeze, which posits that the universe will continue to expand indefinitely. In this model, galaxies drift apart, the cosmos cools, and eventually, stars exhaust their fuel. Over billions of years, the universe would become a vast, dark, and cold expanse where only faint remnants of stars and galaxies exist. A lonely and lifeless ambience where time stretches almost infinitely. Another captivating concept is the Big Crunch, which suggests that if the gravitational pull of matter within the universe is strong enough, it could halt the current expansion and reverse it. This would lead to a gradual collapse where galaxies, stars, and eventually all matter would converge into a singular point. This implosion of cosmic proportions could potentially be followed by another Big Bang, cycling the universe through an endless loop of expansion and contraction. Then there's the Big Rip scenario, which presents a more chaotic end. In this theory, the force driving the universe's expansion, known as dark energy, grows stronger over time. This increased force could tear galaxies apart, further disintegrate stars, and ultimately rip apart atoms themselves. The universe would meet its end not with a whimper or a crunch, but in a violent explosion of separation, resulting in a fragmented and chaotic state. Lastly, the theory of a cyclic universe proposes that rather than ending, our universe undergoes a series of endless expansions and contractions. Each cycle would begin with a Big Bang, leading to a future Big Crunch, followed by another expansion. This repetitive process suggests a universe that continuously evolves and transforms rather than reaching a final destination. While these theories vary widely, they all stem from our understanding of cosmic dynamics, the behavior of fundamental forces, and the intricate fabric of space-time. Each scenario prompts thought-provoking questions about existence, the nature of time, and the fate awaiting our universe, sparking ongoing debates and investigations into the cosmos we inhabit. The heat death of the universe is a fascinating concept centered on the idea of entropy, which is fundamentally a measure of disorder. As time progresses, the universe continues expanding and stars burn through their nuclear fuel, eventually leading to a state where no available energy can be harnessed to perform work. Envision a perfectly balanced game of energy, where every star, planet, and particle contributes to an intricate dance of exchange. Over an unimaginable span of time, all stars will consume their fuel and extinguish. Planets will collide and be absorbed, and black holes will spiral into one another, resulting in an almost uniform distribution of energy across the universe. It's like a once vibrant symphony that slowly fades into a solitary note, devoid of rhythm and harmony. When this ultimate state is reached, the universe would be incredibly cold and dark. All matter would exist in a dispersed manner, unable to interact meaningfully. At this stage, the concept of time itself could lose significance, as there would be no events or activities to measure it against. Photons, which are particles of light, would drift peacefully through a vast ocean of emptiness, carrying with them the last remnants of energy. The heat death signifies a complete transformation of the universe into a lifeless, energy-depleted state, where structure and complexity give way to a monotonous equilibrium. It's a scenario that leaves behind the vibrant cosmos we recognize, depicting a future where the possibilities of creation and movement have long vanished. The Big Rip scenario presents a fascinating and alarming possibility for the ultimate fate of our universe. In this theory, the expansion of the universe accelerates to such an extreme that galaxies, stars, planets, and even atoms are torn apart. Imagine blowing up a balloon. As it expands, the material stretches, and eventually, if it keeps growing, it bursts. In the context of the universe, this means that the forces driving this expansion, specifically dark energy, overcome the gravitational forces that hold matter together. What differentiates the Big Rip from other end-of-universe theories is primarily its dramatic and violent nature. For instance, the Big Crunch suggests that the universe's expansion will eventually slow down and reverse, leading everything to collapse back into a singular point. A contrasting scenario, known as the heat death, posits that the universe will continue to expand until it reaches a state of maximum entropy, a kind of cosmic equilibrium where nothing happens and all organized structures cease to exist. In the Big Rip, however, the end is not gradual. It is chaotic and catastrophic. As the universe expands, the gravitational force that binds systems together, like galaxies or even solar systems, weakens until they can no longer hold. This breakdown progressively affects larger structures, leading ultimately to the disintegration of everything down to the subatomic level. The very fabric of space-time may unravel, culminating in a universe that is nothing but a chaotic swirl of particles. Each of these theories reflects our understanding of different aspects of the universe, but the Big Rip adds a layer of urgency and turbulence, suggesting a future where the universe isn't merely fading silently away, but rather exploding into a tumultuous dissolution. This distinctive aspect of the Big Rip captures the imagination, presenting an end that is not only dramatic but also challenges our comprehension of the forces shaping our cosmic reality. Current and future technologies are playing a crucial role in predicting the distant future of the universe, allowing scientists to gather data and make more informed models than ever before. One of the primary tools at our disposal is the advanced telescopes located both on Earth and in space. These powerful instruments can detect light from stars and galaxies that may have emitted it billions of years ago. By analyzing this ancient light, researchers can understand the composition, age, and motion of celestial bodies, offering a glimpse into how they will evolve over time. Additionally, simulations driven by sophisticated computer models help us visualize the universe's expansive dynamics. These simulations incorporate principles of physics, like gravity and thermodynamics, to model how galaxies merge or how cosmic structures develop. With the incorporation of vast datasets from observational studies, these models can make increasingly accurate predictions about the fate of the universe. For example, will it continue expanding indefinitely, or will gravitational forces eventually pull it back together? Moreover, technologies such as particle accelerators and observatories that probe cosmic background radiation provide insights into the fundamental particles that make up the universe. This research aids in understanding concepts like dark matter and dark energy, which are fundamental to our comprehension of cosmic evolution. As we learn more about these mysterious components, we can better predict how they will shape the universe's future. In the coming years, next-generation observatories, like those designed to explore gravitational waves or conduct large-scale galaxy surveys, promise to unlock even more secrets. These advancements allow us to explore even deeper into the universe's earliest moments and understand complex phenomena, such as cosmic inflation and the formation of structure in the universe. Together, these technologies weave a tapestry of knowledge, enabling scientists to unravel the mysteries of the universe's distant future. As we develop innovative techniques and methodologies, our vision will sharpen, illuminating a future of cosmic exploration unlike anything we have witnessed before. The far future of space exploration and colonization holds exciting possibilities that stretch the imagination. As we continue to develop advanced technologies, we may see humanity establishing a presence on other celestial bodies, such as Mars and the moons of Jupiter and Saturn. Picture vast domes or even entire cities designed to protect us from harsh environments where humans can live, work, and thrive amidst alien landscapes. These habitats would utilize local resources for food, water, and energy, making it possible to sustain life far from Earth. Traveling between planets could transform into a routine venture, much like air travel is today. Spacecraft may be equipped with propulsion systems that allow for quicker journeys, potentially making trips to Mars last just a matter of weeks instead of months. Envision fleets of ships capable of carrying both cargo and people, connecting various outposts across the solar system. As we venture further, settlements could grow into complex societies with their own cultures and systems of governance. The uniqueness of each location might inspire diverse ways of living, influenced by the different environments and resources available. Imagine a bustling trade network linking Earth, Mars, and other settlements, creating a new economic era that spans the cosmos. In the grander scheme, the exploration of exoplanets, those distant worlds in other star systems, could become an integral part of our future. With innovative telescopes and technologies, we may identify viable planets for human habitation. The potential for interstellar exploration is tantalizing. Concepts of generation ships, which could sustain life for many years during the journey, might shift from science fiction to reality as we strive to reach these new worlds. Amid these grand developments, we will likely grapple with ethical considerations surrounding colonization, such as the impact on any existing ecosystems and the rights of future settlers. This balancing act of exploration, discovery, and responsibility will be essential in shaping not just how we expand beyond our home planet, but also how we define our place in the universe. In this envisioned future, humanity may not just be surviving beyond Earth, but flourishing, creating a multi-planetary civilization that continues to explore, innovate, and learn. Space could become a shared stage where human curiosity drives us to unlock the secrets of the universe, advancing our knowledge and experience in ways previously thought impossible. In the vast realms of theoretical physics, quantum mechanics and relativity often appear as two distinct languages, each describing the universe at different scales. Quantum mechanics governs the behavior of the extremely small encompassing particles like atoms and subatomic components. Here, unpredictability reigns, as particles exist in states of probability rather than certainties. This is a world where matter and energy dance in intricate patterns, often defying the rules of classical physics. On the other hand, relativity, articulated by the groundbreaking work of Albert Einstein, shapes our understanding of the cosmos at a grand scale. It describes how massive objects like stars and planets warp the flexible fabric of space and time. In this realm, gravity is not just a force, but rather a consequence of these curved dimensions, leading to phenomena such as time dilation, where time moves slower in stronger gravitational fields. The challenge arises when these two frameworks collide. The intricate workings of the quantum world seem incompatible with the smooth, continuous nature of spacetime described by relativity. This has led physicists to explore theoretical approaches that seek to unify them, one of which is string theory. String theory proposes that the fundamental particles are not merely points, but rather tiny, vibrating strings, with their vibrations determining the type of particle they represent. This approach offers a potential way to incorporate both quantum mechanics and gravity into a single cohesive theory. Another promising area of research is loop quantum gravity, which attempts to quantize spacetime itself. In this framework, spacetime is made up of discrete chunks, suggesting a microstructure that merges quantum principles with gravitational interactions. While a definitive theory that seamlessly marries quantum mechanics with relativity remains elusive, the ongoing investigation into their intersection reflects humanity's innate curiosity about the universe. The goal is not just theoretical, it is about transcending our existing understanding, potentially unlocking secrets of black holes, the origins of the universe, and the very fabric of reality itself. Through this journey, physicists continue to push the boundaries of what we perceive, inching closer to unraveling the mysteries of existence. Quantum entanglement is a fascinating phenomenon that occurs when two particles become linked in such a way that the state of one instantly influences the state of the other, regardless of the distance between them. Imagine two friends who have a special bond. When one laughs, the other instantly feels joyful, no matter how far apart they are. In the quantum world, this connection plays a critical role in how particles interact and communicate. When particles become entangled, measuring the properties of one particle, such as its spin or position, immediately reveals the properties of the other particle. This happens without any signal traveling between them. It's as if they share information in a way that seems to defy the conventional understanding of space and time. This peculiar behavior raises profound questions about the nature of reality itself, challenging the traditional notions of locality and causality that govern our understanding of the universe. The implications of quantum entanglement extend far beyond just fascinating scientific curiosity. It opens the door to revolutionary advancements, particularly in the field of quantum computing and communication. Imagine a computer that could perform complex calculations at speeds unimaginable today, or a communication system that is completely secure against eavesdropping due to the entangled nature of the particles involved. Moreover, exploring entanglement challenges scientists to rethink interconnectedness within the cosmos. It suggests that the universe is not merely a collection of isolated objects, but a vast, intricate web of interrelations. The study of quantum entanglement thus serves as a gateway to deeper inquiries about the fundamental fabric of reality, ultimately propelling us toward a richer and more interconnected understanding of the universe we inhabit. Physicists have long sought a way to unify the fundamental forces of nature. aiming for a single overarching theory that could explain how everything in the universe interacts. Currently, we understand four primary forces: gravity, electromagnetism, and the weak and strong nuclear forces. However, these forces operate under different principles and mathematical frameworks. This is where theories like string theory come into play. String theory proposes that the smallest constituents of matter are not point-like particles, as traditionally thought, but rather tiny, vibrating strings. Imagine these strings as the strings of a musical instrument, each vibration creating different types of particles, which in turn represent different forces and matter. The unique qualities of a string, its length, tension, and vibration, determine the characteristics of the particles it manifests. This fundamental change shifts how we approach the relationships among forces. The beauty of string theory lies in its potential to provide a single framework that can incorporate all four forces. Instead of treating them as entirely separate entities, string theory suggests they are manifestations of the same underlying principles. This theory also requires additional dimensions, more than the three dimensions of space and one of time that we experience daily. These extra dimensions, while difficult to visualize, allow for complex interactions between the strings that could unify the forces. Beyond string theory, physicists are exploring other models, such as loop quantum gravity, which attempts to merge general relativity and quantum mechanics without the need for additional dimensions. These researchers are experimenting with the fabric of space-time itself, visualizing it as a network of tiny loops that form the structure of the universe, enabling them to study how gravity might behave at the quantum level. While string theory has yet to be confirmed through experimental evidence and remains a highly theoretical pursuit, it illuminates a path toward understanding the universe's fundamental workings. As physicists continue to probe these concepts, they hope to reveal a unified theory that resonates with both the microscopic world of particles and the vast cosmos. Each advancement in this quest not only deepens our comprehension of nature, but also draws us closer to the answers that have eluded humanity for centuries. The concept of the multiverse presents a profound shift in how we think about existence itself. Traditionally, we perceive the universe as a singular entity, the vast space containing everything we know, from the smallest particles to the largest galaxies, all governed by universal laws. However, the multiverse theory suggests that our universe might just be one of countless others, each with its own unique properties, physical laws, and even different dimensions of time and space. Imagine each universe as a bubble within a vast ocean of possibilities. Some of these bubbles may be similar to ours, where conditions allow for life to exist, while others might be drastically different, harboring forms of matter and energy that we can't yet comprehend. This idea challenges our understanding in several ways. It raises questions about what it means to exist, as we may no longer be the center of all things, but merely one outcome among an infinite array of alternatives. The implications go further, delving into the nature of reality itself. If there are parallel universes, the choices we make might create divergent paths, resulting in a version of ourselves that has taken a different direction in a different universe. This notion prompts us to reconsider free will and destiny, leading to fascinating philosophical debates. Additionally, the multiverse challenges the predictability and uniformity we often apply to scientific laws. In our universe, we can observe and measure phenomena based on consistent rules. Yet, if other universes operate under different laws, what we consider fundamental truths might only be applicable to our own bubble. Ultimately, the multiverse theory expands the very fabric of reality, inviting us to explore the unknown depths of existence. It encourages curiosity about what lies beyond our observable horizon, paving the way for new scientific inquiries and philosophical reflections on life, choice, and the essence of being. Quantum fluctuations played a crucial role in shaping the early universe immediately following the Big Bang. To grasp their significance, picture the universe as a vast, boiling pot of energy and particles, where at the smallest scales, nothing is ever truly still. Instead, particles pop in and out of existence due to the inherent uncertainties of quantum mechanics. This activity occurs everywhere, even in the empty vacuum of space. In the infant universe, these minute fluctuations created tiny variations in density, acting like seeds for the structures we see today: galaxies, stars, and planets. When matter began to gather due to gravitational attraction, the fluctuations facilitated this process by providing the initial jiggles, rich patches of potential matter surrounded by voids. Over time, as the universe expanded and cooled, these slight differences became magnified, allowing matter to accumulate and evolve into the complex cosmic web we observe. Additionally, the idea of inflation, a rapid expansion of space that occurred very early in the universe's history, links directly to these quantum fluctuations. During inflation, the universe grew exponentially in size, stretching those minuscule initial variations across vast distances. The result was a nearly uniform universe with slight irregularities that would eventually give rise to complex structures. Quantum fluctuations are fundamental to understanding the universe's evolution from a hot, dense state to the diverse cosmos we inhabit today. They serve as the building blocks of matter, influencing the overall shape and development of the universe, marking the bridge between the quantum realm and the vast, observable universe. Throughout history, human perceptions of the universe have undergone profound transformations, shaped by advances in knowledge, technology, and philosophy. In ancient times, many cultures viewed the cosmos through a lens of mythology and spirituality. The stars were seen as deities or as messages from the divine. Civilizations, like the Greeks and the Babylonians, created intricate stories to explain the workings of the universe, attributing celestial phenomena to the actions of gods. As humanity began to observe the sky more systematically, our understanding began to shift. The advocacy of a heliocentric model, suggesting that the Earth orbits the Sun, marked a revolutionary moment. This idea, championed by thinkers such as Copernicus and later validated by Galileo's telescopic discoveries, challenged long-held beliefs that placed Earth at the center of the universe. This transition was not merely scientific, it represented a profound philosophical shift toward rationalism and empirical observation. With the Age of Enlightenment came further advancements. Scientists like Newton laid the groundwork for modern physics, introducing laws of motion and universal gravitation that unified the heavens and earth under common physical principles. The cosmos began appearing less as a realm of the divine and more as an orderly system that could be understood through reason and observation. In the 20th century, our perceptions continued to evolve dramatically. The discovery of the expanding universe, leading to the concept of the Big Bang, shifted our understanding of the cosmos from a static entity to a dynamic, evolving reality. Technological innovations like radio telescopes and space telescopes allowed us to peer deeper into space and time, revealing galaxies, black holes, and cosmic microwave background radiation, the afterglow of the universe's birth. Today, we view the universe as a vast tapestry of interconnected phenomena, shaped by the interplay of matter, energy, and the fundamental forces. The knowledge of dark matter and dark energy compels us to rethink our existence within this grand structure. We comprehend that we inhabit just a tiny fraction of an incomprehensibly vast cosmos. As we continue to ask questions and seek answers, our perspective of the universe will inevitably transform once again, urging humanity to expand its understanding and redefine its place among the stars. Mythology and storytelling have profoundly shaped our understanding of the cosmos throughout history. In ancient times, as humans gazed up at the night sky, they encountered awe-inspiring celestial phenomena that sparked their imaginations. They crafted stories and legends, attributing behaviors and characteristics to stars, planets, and constellations. These narratives not only served to explain the inexplicable, but also provided a framework for societies to understand their place in the universe. For example, many cultures viewed celestial bodies as deities or spirits, creating myths that reflected their values, beliefs, and fears. The patterns observed in the night sky were interpreted through these stories, allowing people to gain insight into seasonal changes, navigation, and timekeeping. The stars became a canvas where human experiences were projected. Triumphs, disasters, and the common struggles of existence were interwoven with the cosmos. As civilizations evolved, these myths contributed to early scientific thought. The need to understand celestial events led to the development of astronomy. Observations about the movements of planets and the phases of the moon emerged from these rich narratives. However, the interplay between mythology and science did not sever. Instead, they often existed in tandem, enriching our perspectives on the universe. In modern times, even as scientific understanding has advanced, the narratives surrounding the cosmos continue to resonate. They inspire curiosity about the origins of the universe, the nature of black holes, and the possibility of extraterrestrial life. Science fiction, for instance, draws heavily upon the mythic tradition, allowing us to dream about interstellar travels and the future of humanity among the stars. Such storytelling fosters a connection to the cosmos, inviting us not just to observe, but to reflect on the profound mysteries of existence and our aspirations as a species. Thus, mythology and storytelling are not merely relics of the past. They are vital threads in the tapestry of human understanding, connecting culture, imagination, and scientific inquiry in a way that continues to enrich our exploration of the universe. Cultures around the world have long gazed at the night sky, interpreting celestial phenomena in myriad ways that reflect their values, beliefs, and experiences. For many ancient civilizations, such as the Mayans and Egyptians, the movements of the stars and planets dictated agricultural practices, religious ceremonies, and societal calendars. They saw the celestial bodies not merely as distant lights, but as divine entities or messages from the gods. In some cultures, certain constellations represent important figures from mythology. For instance, in Greek mythology, Orion is depicted as a mighty hunter, while in various indigenous cultures, the same set of stars may symbolize a significant animal, spirit, or ancestral figure. These stories bind people to their heritage and serve as a way to pass down knowledge through generations. In the Pacific Islands, navigators looked to the stars for direction during their ocean voyages. The ability to read the night sky allowed them to travel vast distances, transforming celestial events into practical tools for navigation, reflecting a deep connection between culture, survival, and the universe. Moreover, different interpretations can arise from the same astronomical event. A solar eclipse, for example, may evoke fear and awe in one culture, symbolizing an omen or a time for ritual cleansing, while another culture might see it as a manifestation of cosmic balance or celebration. In contemporary times, while many cultures have embraced scientific reasoning to explain astronomical phenomena, the rich tapestry of stories and interpretations continues to hold a captivating place in human experience, merging the scientific with the spiritual and cultural. This blend illustrates how, across time and space, the universe serves as a canvas for human imagination and understanding, continually shaping our cultural identities. Art and literature play a crucial role in exploring and expressing the mysteries of the universe, acting as bridges between complex scientific concepts and the human experience. While science provides the factual backbone, data and theories, art and literature engage our emotions, imaginations, and curiosity. They allow us to ponder not just what the universe is, but what it means to us as human beings. Through storytelling, authors can illustrate the grandeur of cosmic phenomena or the intricacies of evolution in accessible ways. A beautifully crafted narrative can evoke the wonders of a distant galaxy, transforming abstract ideas into vivid images. Poetry can capture the awe of a starry night, making the vastness of space feel intimate and relatable. Such creative expressions invite us to reflect on our existence, our place in the cosmos, and the complex emotions that arise from contemplating the unknown. Additionally, art serves as a catalyst for inquiry. When an artist imagines alien worlds or fantastical interpretations of black holes, it ignites questions and discussions that lead us to explore the actual science behind those visions. This interplay between imagination and reality can inspire future scientists, provoke philosophical debates, and encourage a sense of wonder that fuels lifelong curiosity. In a world driven by technology and empirical data, art and literature remind us that the quest to understand the universe is not solely about numbers and equations. It's about the stories we share, the emotions we feel, and the connections we make with the vast cosmic landscape around us. They encourage us to seek answers, embrace the mysteries, and celebrate the profound beauty that the universe offers. Through these mediums, the enigma of the cosmos transforms from a mere intellectual exercise into a shared human journey. Modern scientific discoveries often illuminate age-old questions about existence and meaning in fascinating ways. At the heart of humanity's quest for understanding lies the fundamental inquiry: why are we here? Natural sciences such as astronomy and biology have made significant advances that inform this timeless contemplation. For example, the exploration of the universe has revealed vast galaxies, each containing billions of stars and planets. This knowledge shifts our perspective on our own existence, encouraging us to see ourselves not as separate from the cosmos, but as integral parts of its grand narrative. The discovery of exoplanets, worlds orbiting other stars, sparks questions about life beyond Earth, inviting us to ponder whether we are unique or part of a larger tapestry of existence. On a different front, evolutionary biology has unraveled the intricate processes that led to the development of life on our planet. Understanding evolution portrays life as a dynamic story of adaptation and survival rather than a static creation. It compels us to think about our purpose in a profound context, a continuum of life shaped by environment, time, and chance. Additionally, advancements in quantum physics challenge conventional notions of reality and existence. They hint at the possibility that at the most fundamental level, our understanding of reality is blurred and interconnected in ways we are only beginning to grasp. This capacity for contradiction raises inquiries about free will, consciousness, and our roles in a universe governed by laws that often seem strange and paradoxical. Together, these scientific revelations do not extinguish the philosophical and existential questions. Rather, they add depth and complexity to them. They encourage a dialogue between the scientific and the philosophical, allowing a rich exploration of concepts such as consciousness, purpose, and the very nature of reality. In this intersection, science and philosophy both serve to expand our understanding of existence, highlighting that as we uncover more about the universe, we are also diving deeper into the essence of our own humanity. Modern astronomy has seen remarkable technological advancements that have transformed our understanding of the universe. One of the most significant developments is the rise of telescopes that operate in various wavelengths of light. While traditional optical telescopes capture visible light, new telescopes can detect infrared, ultraviolet, and even radio waves. This allows astronomers to gather information about celestial bodies that are otherwise invisible, revealing hidden details about their composition and behavior. Another major advancement is the use of space-based observatories. Placing telescopes beyond Earth's atmosphere removes the interference caused by air pollution and weather, resulting in clearer and more precise observations. For example, the Hubble Space Telescope has captured breathtaking images and provided invaluable data about galaxies, nebulae, and exoplanets, expanding our knowledge beyond what ground-based telescopes could achieve. Digital imaging technology has also revolutionized astronomy. Sophisticated cameras equipped with sensitive detectors can collect light over extended periods, enabling astronomers to spot faint objects that were previously undetectable. The ability to process and analyze large data sets has introduced new ways to study the universe, including methods that utilize artificial intelligence to identify patterns and anomalies in vast amounts of data collected by surveys. Moreover, advancements in computer simulations and modeling have allowed scientists to better understand complex cosmic phenomena, from the formation of stars to the dynamics of galaxies. These powerful computational tools provide insights that observational data alone cannot achieve, helping to form predictions and guide future exploration. Lastly, the development of autonomous robotic telescopes and observatories has opened up new opportunities for exploration. These systems can conduct observations without constant human supervision, allowing for continuous observation of celestial events such as supernovae or the passage of asteroids. These advancements, through collaboration among physicists, engineers, and astronomers, continue to propel our quest for knowledge, providing a clearer window into the vast, intricate tapestry of our universe. Radio telescopes have fundamentally transformed the way we explore and comprehend celestial objects, allowing us to perceive the universe in a light invisible to the naked eye. Unlike optical telescopes that capture visible light, radio telescopes detect radio waves emitted from various cosmic sources. This capability enables scientists to gather information about phenomena unreachable by other means. One of the most significant contributions of radio telescopes is their ability to peer through cosmic dust and gas that obscure visible light. For instance, they can observe the centers of galaxies, where massive black holes lurk, revealing dynamic activities that light-based observations might miss. By analyzing the emitted radio waves, researchers gain insights into the structure, composition, and behaviors of both stars and galaxies, opening up a realm of astronomical phenomena such as pulsars and quasars. Furthermore, radio telescopes have led to groundbreaking discoveries in the field of cosmic microwave background radiation. This remnant radiation from the early universe provides essential details about its formation and evolution. Through detailed studies, astronomers can piece together the timeline of the cosmos, enhancing our understanding of concepts like the Big Bang and the universe's expansion. The advent of arrays of radio telescopes, such as the Very Large Array, allows for even more sophisticated observations. These networks of multiple radio dishes work together to form a single powerful telescope, improving the clarity and resolution of images. This technique, known as interferometry, elevates our ability to discern finer details in the cosmic tapestry, unraveling complex structures and interactions within the universe. Radio telescopes are also integral to the search for extraterrestrial intelligence. They scan the heavens for potential signals from other civilizations, exploring the age-old question of whether we are alone in the universe. This search not only fosters a deeper curiosity, but amplifies the quest for understanding life beyond Earth. Radio telescopes act as windows to a different realm of cosmic understanding, unveiling phenomena and details that are obscured to other forms of observation. By broadening our perspective on the universe, they continue to inspire awe, curiosity, and a deeper comprehension of our place in the cosmos. Citizen scientists have become invaluable contributors to the field of astronomy, transforming the way we explore and understand the cosmos. These enthusiastic individuals, often without formal training in science, gather, analyze, and share astronomical data, enriching research efforts in ways that professional scientists alone could not achieve. By participating in various projects, citizen scientists assist with tasks such as classifying celestial objects, reporting observations of transient astronomical events, and even searching for exoplanets. Many of these initiatives are available online, allowing people from all walks of life to engage with astronomy from their own homes. This accessibility democratizes science, inviting countless individuals to contribute to the biggest questions about our universe. One striking example is the work accomplished through organizations that crowdsource observations of particular phenomena, such as variable stars or supernovae. Citizen scientists can monitor these objects, contributing to real-time data that researchers depend on to further understand their behavior. Because these volunteers work on an enormous scale, they can uncover patterns and anomalies that might be missed by a smaller team of scientists. Moreover, citizen scientists often bring diverse perspectives and insights. Their varied backgrounds can inspire innovative approaches to research problems. The collaboration between amateurs and professionals facilitates a symbiotic relationship where professional astronomers guide citizen scientists while also benefiting from their fresh enthusiasm and new ideas. Ultimately, the role of citizen scientists in astronomy is essential. They serve as a bridge between the scientific community and the public, igniting interest in space exploration and fostering a deeper appreciation for the universe. By harnessing the collective efforts of countless passionate individuals, the field of astronomy continues to advance, uncovering secrets and mysteries that can only be revealed through collaboration. Spectroscopy is a powerful tool that allows scientists to unravel the secrets of distant stars and planets by examining the light they emit or reflect. When light travels from a celestial object, it can be split into its component colors, much like how a prism reveals a rainbow. This separation creates a spectrum, a unique fingerprint of light that conveys valuable information about the object's composition. Each chemical element emits or absorbs light at specific wavelengths, which appear as bright or dark lines within the spectrum. By studying these lines, astronomers can identify which elements and molecules are present in a star or planet's atmosphere. For example, a line might indicate the presence of hydrogen, while another could signal the existence of methane. This method is akin to analyzing a recipe by identifying each ingredient based on distinct flavors. Additionally, the spectrum can reveal temperature, density, mass, distance, luminosity, and relative motion of the object of study. A phenomenon known as the Doppler effect comes into play here. If a star is moving towards us, its light shifts toward shorter wavelengths, making it appear bluer, while light from a star moving away shifts to longer wavelengths, appearing redder. This movement not only gives insights into the star's velocity, but can also hint at the presence of orbiting planets. By piecing together the myriad of details provided by spectroscopy, scientists form a comprehensive understanding of the building blocks of the universe, shedding light on the fundamental processes that govern stars and planets far beyond our own solar system. In this way, spectroscopy acts as a window into the cosmos, allowing us to see and comprehend what lies beyond our reach. The future of space telescopes, like the James Webb Space Telescope, is promising and full of potential to revolutionize our understanding of the universe. This powerful observatory is designed to explore the cosmos in ways that previous telescopes could not, especially in the infrared spectrum. By detecting light that has traveled billions of years to reach us, it allows scientists to peer back in time, observing the first galaxies that formed after the Big Bang. As we look ahead, the James Webb Space Telescope will play a crucial role in addressing some of the most profound questions in astronomy. It is expected to enhance our understanding of how stars and planets form, providing insight into the processes that lead to the emergence of life. With its ability to study the composition of exoplanet atmospheres, it may help identify the building blocks necessary for life beyond our own planet and assess the conditions of distant worlds. Moreover, the telescope will facilitate groundbreaking studies of phenomena like dark matter and dark energy, two mysterious constituents of the universe that shape its expansion and structure. By making detailed observations of galaxies and their interactions over time, Webb will help unravel the mysteries behind the evolution of cosmic structures, potentially reshaping our understanding of the universe's history. In addition to its direct contributions to astrophysics, the James Webb Space Telescope is part of a larger trend in space exploration. Its findings will serve as a foundation for future observatories and missions, guiding the development of new technologies and methodologies in the field. The data generated by Webb will be invaluable for researchers around the world, sparking further inquiry and collaboration. The James Webb Space Telescope is not just a remarkable instrument. It is a key to unlocking the mysteries of the universe and a stepping stone towards deeper cosmic exploration. Its legacy will extend well beyond its operational life, influencing generations of scientists and space enthusiasts alike. Cosmic events have played a crucial role in the development of Earth and the evolution of life over billions of years. One of the earliest and most significant events was the formation of the Earth itself. Around 4.5 billion years ago, our planet formed from the debris left over after the birth of the Sun. This process, known as accretion, involved countless collisions with other space materials, imparting heat and leading to the creation of a molten world. As Earth cooled, cosmic impacts continued to shape its surface. Asteroids and comets bombarded the planet, creating craters and influencing the environment. For instance, the delivery of water and organic molecules from these icy bodies may have been essential for the emergence of life. It's believed that the rich mix of elements brought to the early Earth through these impacts was a fundamental contributor to the conditions necessary for life to evolve. Moreover, the influence of the Moon, formed shortly after Earth's creation from a colossal impact, has drastically affected Earth's stability. The Moon stabilizes Earth's tilt, which helps regulate the climate, affecting weather patterns and the seasons. This stable environment has been crucial for the development of diverse ecosystems over billions of years. Moving forward in time, large-scale cosmic events such as supernovae also contributed to Earth's life by enriching the solar system with heavier elements necessary for forming planets and ultimately organic life. Supernova explosions scatter elements like carbon and iron throughout space, creating the building blocks for life as we know it. The past few billion years have not been without catastrophic events that shaped both the planet and its inhabitants. Asteroid impacts, like the one that is believed to have caused the extinction of the dinosaurs, dramatically altered ecosystems and opened niches for new species to thrive. These kinds of mass extinction events, often triggered by collisions with celestial bodies, have repeatedly reset the course of life on Earth. Cosmic events have not only sculpted the physical characteristics of our planet, but have also catalyzed major shifts in biological diversity. Each impact, each burst of stellar energy has contributed to the dynamic and ever-changing tapestry of life, guiding its journey from simple organisms to the complex ecosystems we see today. Thus, Earth stands as a testament to the ongoing interplay between the cosmos and the life it has nurtured for eons. Supernovae play a crucial role in the cosmic cycle of elements, particularly those essential for life. When a massive star reaches the end of its life cycle, it undergoes a dramatic explosion known as a supernova. This cataclysmic event is not just a spectacular light show, it serves as a powerful mechanism for dispersing heavy elements throughout space. As a star evolves, it fuses lighter elements into heavier ones in its core, creating metals such as carbon, oxygen, and iron, elements vital for life as we know it. When the star can no longer sustain nuclear fusion, it collapses under its own gravity and then explodes. During this explosion, the intense heat and pressure facilitate the synthesis of even heavier elements, like gold and uranium, through rapid neutron capture processes. In the aftermath of a supernova, the outer layers of the star are expelled into the surrounding interstellar medium, enriching it with these newly formed elements. This cosmic recycling process means that the materials necessary for planets, and ultimately life, are scattered across vast regions of space. Over time, these elements can accumulate in molecular clouds, leading to the formation of new stars and planetary systems. Without supernovae, the abundance of heavier elements in the universe would be significantly lower. Their explosions are fundamental to the creation of the building blocks of life, ensuring that when new stars and planets form, they have access to the diverse range of elements needed for chemical complexity and, ultimately, the emergence of life. Thus, supernovae act as both destroyers and creators, enabling the dynamic process that leads to the rich tapestry of the universe, including the conditions necessary for life. Gamma-ray bursts are incredibly powerful explosions that occur in distant galaxies, often signaling the death of massive stars. These bursts unleash a tremendous amount of energy, which can have profound effects on their surrounding environments. When a gamma-ray burst radiates through space, it can impact nearby gas and dust clouds, the very materials that form new stars. The intense energy from a gamma-ray burst can compress these clouds of gas, enhancing the conditions necessary for star formation. Imagine pushing a pile of snow. The force can shape it into compact forms. Similarly, the shock waves generated by the burst can trigger a chain reaction, causing portions of the gas to collapse under their own gravity. This leads to the formation of new stars and possibly even clusters of stars, altering the star formation landscape of the galaxy. However, the effects are not solely constructive. A nearby gamma-ray burst can also strip away gas from surrounding areas and even disrupt existing star formation processes. The explosion's energy can heat the surrounding materials to extreme temperatures, making it more difficult for new stars to condense from the remaining gas. This dual nature emphasizes that while gamma-ray bursts can ignite new stellar activity, they can also quench it. In addition, the environment created by a gamma-ray burst can lead to higher rates of fusion in newly forming stars, potentially producing a range of heavier elements. These elements are crucial as they spread throughout galaxies, enriching the interstellar medium, the gas and dust between stars, with the building blocks necessary for forming planets and life. Overall, gamma-ray bursts serve as cosmic catalysts and disruptors, shaping the star formation and evolution of galaxies in complex and dynamic ways. This dynamic interplay illustrates the often chaotic nature of galaxy development, showing how monumental events in the universe can set in motion a cascade of changes that influence the very fabric of stellar life. Cosmic rays, high-energy particles that originate from outside our solar system, can have profound effects on planetary atmospheres and the potential for life. As these energetic particles penetrate the atmosphere, they interact with atoms and molecules, causing a series of reactions that can lead to the formation of secondary particles like muons and neutrons. This interaction is significant because it can alter the chemical composition of the atmosphere. For instance, when cosmic rays collide with nitrogen and oxygen in the air, they can produce ozone and other reactive gases. While ozone in the upper atmosphere plays a protective role, shielding life from harmful ultraviolet radiation, an excess of other reactive chemicals can lead to atmospheric changes that might be detrimental to life. Elevated levels of these chemicals could contribute to temperature fluctuations and disrupt weather patterns, potentially impacting ecosystems. Moreover, cosmic rays may have direct and indirect consequences on potential life forms. On one hand, the high-energy particles can damage the DNA of living organisms. This damage could lead to mutations, which are sometimes deleterious, potentially threatening species survival. On the other hand, in some environments, cosmic rays can trigger molecular changes that might spark biochemical reactions essential for life, possibly even contributing to the origins of life in the deeper reaches of space. Planetary bodies without a protective magnetic field, like Mars, are particularly vulnerable. The thin Martian atmosphere offers minimal shielding against cosmic rays, exposing the surface to high levels of radiation. This heightened exposure could limit the potential for life or make survival extremely challenging for any microbes that might exist. Cosmic rays wield a dual-edged sword when it comes to planetary atmospheres and the potential for life. They are capable of altering atmospheric chemistry in ways that can either hinder or possibly facilitate the conditions necessary for life. Understanding how these extraterrestrial particles interact with planetary environments remains crucial in the search for life beyond Earth. Asteroid impacts can have dramatic and lasting effects on planetary climates and the course of biological evolution. When a sizable asteroid collides with a planet, it releases an enormous amount of energy, equivalent to the explosion of millions of nuclear weapons. This energy creates shock waves, generates intense heat, and launches debris into the atmosphere. The immediate aftermath of such an impact can be catastrophic. The heat can ignite wildfires, while the shockwave can create tsunamis and destroy ecosystems. More perilous, the debris thrown into the atmosphere can block sunlight, leading to what scientists call a nuclear winter effect. This drop in temperatures can last for months or even years, severely disrupting photosynthesis and precipitating a collapse in food chains. The most famous example of this is the asteroid that struck Earth around 66 million years ago, which is widely believed to have led to the mass extinction of the dinosaurs. The impact set off a chain of events that drastically changed the climate, killing off many species and paving the way for mammals to rise and thrive in the absence of dominant reptiles. Over longer periods, the dust and gases from asteroid impacts can alter the atmosphere itself, potentially influencing rainfall patterns and temperatures. When conditions change, organisms adapt or perish. This changing landscape may lead to new evolutionary paths, as species that can cope with altered environments thrive while others go extinct. Each asteroid impact serves as a reset button of sorts, reshaping ecosystems and influencing which life forms prevail. These events can lead to innovation in evolution, allowing life to adapt to new challenges, sometimes resulting in the emergence of entirely new species. Thus, asteroid impacts are pivotal moments in the history of planets, serving as both destructive forces and catalysts for biological diversity. Solar cycles, characterized by the regular increase and decrease in sunspot activity, have played a significant role in shaping Earth's climate over the millennia. These cycles typically span about 11 years, during which variations in solar energy output occur. The Sun emits more energy during periods of high sunspot activity, while lower activity levels correspond with less energy output. Throughout history, these fluctuations have had noticeable effects on Earth's temperature and climate patterns. For instance, during periods of heightened solar activity, known as solar maximum, the additional energy can lead to warmer conditions on Earth. This has been linked to climatic phenomena such as milder winters and changes in precipitation patterns. In contrast, during solar minimum, when sunspots are scarce, the reduced solar output may contribute to cooler temperatures. The Little Ice Age, spanning several centuries from the late Middle Ages to the 19th century, is thought to have coincided with periods of decreased solar activity, as well as volcanic eruptions that released ash and gases into the atmosphere, further cooling the planet. It's important to see solar cycles as part of a broader canvas of influences on Earth's climate, which include volcanic activity, variations in ocean currents, and human impacts. Solar cycles interact with these factors to create a complex system that shapes long-term climate changes. Understanding these cycles helps scientists piece together the historical puzzle of climate variations and predict future trends in a world undergoing rapid changes. Future solar events, such as solar flares and coronal mass ejections, have the potential to significantly disrupt electrical and satellite systems on Earth. The Sun constantly emits a stream of charged particles known as solar wind. Occasionally, this activity escalates into more intense events that can throw vast amounts of energy and charged particles into space. When these particles reach Earth, they interact with our magnetic field, which serves as a protective shield. However, during strong solar events, this shield can be compromised, leading to what scientists refer to as geomagnetic storms. These storms can induce powerful currents in electrical grids, potentially causing transformers to overheat and, in extreme cases, leading to widespread power outages. Infrastructure that relies on continuous power, hospitals, communications, and transportation could face serious consequences. Additionally, satellite systems are at risk as well. Satellites orbiting Earth are exposed to intense radiation during solar storms. This can interfere with their delicate electronics and, in some situations, degrade the satellite's functionality or even damage them entirely. The GPS system, which many rely on for navigation, can also be affected, leading to inaccurate positioning data during heightened solar activity. Furthermore, communication signals can suffer disruption. The radio waves that carry important data can become distorted or absorbed when solar events increase the ionization in the Earth's upper atmosphere and affect the layers crucial for signal transmission. This can lead to intermittent or complete loss of communication, impacting everything from commercial airlines to maritime operations. As we look to the future, developing infrastructure to better withstand these solar events will become increasingly important. Continuous monitoring of solar activity and improved forecasting techniques could help mitigate the effects, ensuring that we remain connected and powered even when our sun throws a cosmic tantrum. Magnetars are a rare and extraordinary type of neutron star known for possessing exceptionally strong magnetic fields, far more powerful than what we encounter on Earth. To understand what this means, consider that a neutron star is formed when a massive star exhausts its nuclear fuel, collapsing under its own gravity. However, as this core collapses, it not only becomes incredibly dense, but also carries over some of the original star's magnetic field, which can amplify into astonishing strengths in magnetars. These magnetic fields are so intense that they can influence the electromagnetic environment far beyond their physical size. For instance, a magnetar's magnetic field could potentially affect nearby planets, including Earth if it were sufficiently close. The activity generated by these stars includes violent outbursts of energy, known as soft gamma-ray repeats, which release enormous amounts of high-energy radiation. Should a magnetar's activity occur relatively close to Earth, it could have profound effects. The intense radiation emitted might disrupt our atmosphere, damaging the ozone layer that protects us from harmful solar and cosmic radiation. This could lead to increased levels of radiation exposure on the surface, which might impact both human health and ecological systems. Additionally, there's the potential for severe disturbances in technology. Satellite communications and power grids could face substantial disruptions due to the energetic particles and radiation from a magnetar. While magnetars exist in the far reaches of our universe, their extraordinary powers pose intriguing questions about planetary safety and cosmic interactions, reminding us of the complex and sometimes precarious relationship between celestial phenomena and life on Earth. The Northern Lights, or aurora borealis, are a mesmerizing display of natural light that showcases the intricate relationship between space and Earth. This phenomenon originates from the Sun, which constantly emits energy and particles in what is known as the solar wind. As this stream of charged particles travels through space, some of them encounter Earth's magnetic field, creating a fascinating interaction. Imagine Earth surrounded by an invisible protective shield created by its magnetic field. When the solar wind rushes towards this shield, some particles are redirected towards the poles. As these charged particles, mainly electrons, descend into the upper atmosphere, they collide with gases such as oxygen and nitrogen. These collisions excite the gas molecules, causing them to release energy in the form of light, resulting in those vibrant green, pink, and purple hues that dance across the sky. This interplay between the Sun's activity and Earth's magnetic field not only produces beautiful visuals, but also serves as a reminder of the dynamic forces at play in the cosmos. The Northern Lights vividly illustrate how our planet is not a solitary entity, but part of a larger system where solar phenomena can have a direct impact on life on Earth. The aurora borealis is a captivating testament to the ongoing and intricate connection between the cosmos and our home planet. Tsunamis and meteor showers might seem like events that belong in entirely different realms, one being a powerful ocean phenomenon and the other a cosmic display in the night sky. However, they both illustrate the intricate interconnectedness of Earth and the universe around it. Tsunamis are primarily caused by underwater disturbances such as earthquakes, volcanic eruptions, or even landslides. When these disturbances happen, they displace massive amounts of water, creating waves that can travel across entire ocean basins. This connection to seismic activity is crucial, as many of the forces at play on Earth's surface have their origins deep within its crust. On the other hand, meteor showers occur when the Earth passes through streams of debris left by comets or asteroids. These tiny fragments enter the atmosphere at high speeds, creating bright streaks of light as they vaporize. When we experience a meteor shower, it's a tangible reminder of Earth's relationship with the larger solar system. Events happening millions of kilometers away can directly influence what we see from our planet. Both phenomena evoke the theme of energy transfer and the ripple effects of events. A seismic tremor releasing energy beneath the ocean can result in catastrophic waves, while the arrival of space debris emphasizes how celestial mechanics impact our atmosphere and surface. Through these events, we learn that Earth is not an isolated entity, but an active participant in the cosmic dance of creation and destruction, an intersection of terrestrial and celestial forces where changes in one can have profound effects on the other. This interconnectedness reveals how mammals, ecosystems, and even human beings are shaped by the dynamic interplay between the Earth itself and the vast universe surrounding it. The anthropic principle plays an intriguing role in modern cosmology by suggesting that the universe's physical laws and constants are structured in a manner that accommodates the existence of life, particularly human life. Essentially, it posits that the universe must have properties that allow observers like us to exist. If it didn't, we wouldn't be here to notice it. At its core, the principle can be viewed in two main ways. The weak anthropic principle simply highlights that the conditions we observe in the universe must be compatible with our existence as conscious beings. For example, if the strength of gravity were slightly different, stars might not form, and consequently, planets like Earth could not exist to harbor life. This perspective reinforces our understanding of the universe's intricate balance and the fine-tuning of its fundamental features. On a deeper level, the strong anthropic principle raises more provocative ideas. It suggests that the universe must have properties that inherently support the development of conscious life. This brings us to some of the most exciting realms of contemporary cosmological thought, such as the multiverse theory, which posits that our universe is just one among many diverse, perhaps even infinite universes, each with slightly different physical laws. In such a scenario, it is no surprise that we find ourselves in a universe that permits life. We exist specifically in that universe. The implications of the anthropic principle extend into various discussions in cosmology, including the nature of dark energy, the formulation of theories regarding cosmic inflation, and the exploration of the universe's ultimate fate. It introduces a philosophical dimension to scientific inquiry, prompting questions about why the universe operates as it does and how those conditions interact with the life's narrative within it. By blending observation with existential significance, the anthropic principle encourages a deeper exploration of our place in the cosmos and the mysteries that lie beyond our current understanding. The holographic principle is a revolutionary concept that suggests the universe can be understood as a two-dimensional information structure projected onto a cosmic boundary, while what we perceive as three-dimensional space is illusory. To grasp this idea, imagine a hologram. What appears as a full, three-dimensional image is actually stored in two dimensions. In a similar way, the principle posits that all the information of our three-dimensional experience is encoded on a distant surface, challenging our traditional ideas of space and reality. This perspective reshapes how physicists approach the concepts of gravity and quantum mechanics. It implies that rather than viewing them as entirely separate realms, there may be a deep connection underlying their apparent differences. By suggesting that the fabric of reality at its most fundamental level is actually two-dimensional, physicists are exploring new ways to understand black holes and the very nature of information itself. The holographic principle also raises profound philosophical questions about existence and observation. If the universe's three-dimensional manifestations are essentially projections from a simpler structure, what does that mean for our understanding of reality? It prompts us to reconsider the nature of physical laws and the role of observation in shaping the universe. As researchers delve deeper, the holographic principle not only invites us to reconceptualize the universe, but also hints at a more unified theory of physics that could unite the forces of nature under a common framework, possibly revealing mysteries of the cosmos we are yet to fathom. Loop quantum gravity and its potential alternatives to string theory are at the forefront of theoretical physics, working to unravel the complexities of the cosmos. Loop quantum gravity seeks to merge the principles of quantum mechanics with gravity, proposing that space itself has a discrete structure. Imagine space as a fabric woven from tiny loops, each representing a fundamental unit of area. This means that space isn't smooth, but instead is like a tightly knit tapestry, with quantized patches unfolding in what was once thought to be a continuous entity. This framework alters our understanding of how gravity operates at the smallest scales. Traditionally, gravity is described by the theory of general relativity, which views it as a smooth curvature of space-time. However, when we apply quantum mechanics rules at these small scales, everything gets a bit fuzzier. Loop quantum gravity suggests that, rather than shrinking to infinitely small points, particles and forces are built from these discrete loops, potentially avoiding some paradoxes that often arise in other models of physics. On the other hand, alternatives to string theory also approach the fabric of the universe from different angles. For instance, some researchers investigate how gravity might emerge from the interactions of more fundamental quantum fields rather than being an intrinsic force. This perspective can offer profound insights into the nature of space-time itself, suggesting it could be an emergent property of deeper, unified physics. These theories encourage us to reconsider our motivations for understanding the universe. Instead of merely fitting theories into existing frameworks, they take bold steps toward fundamentally redefining what we understand about reality. By exploring the intersections of these theories, scientists can investigate profound questions, such as the nature of black holes or the behavior of cosmic events at the dawn of the universe. Each of these theories embodies a unique vision of what the cosmos looks like, inviting exploration and debate. They represent humanity's enduring quest to comprehend the universe's most mysterious underpinnings, challenging and enriching our perspective of existence itself. The discovery of the Higgs boson marked a monumental moment in the field of particle physics and fundamentally changed our understanding of the universe. At its core, the Higgs boson is associated with the Higgs field, a background field that exists everywhere in the universe. This field plays a crucial role in explaining how other fundamental particles acquire mass. Imagine the universe as a vast cosmic ocean, where some particles move through the Higgs field smoothly, like fish swimming effortlessly through water. These particles, such as photons, which are the carriers of light, remain massless and can travel at the speed of light. Other particles, however, interact more strongly with the Higgs field, akin to objects pushing against the water. This interaction results in those particles gaining mass, allowing them to form the building blocks of matter, from atoms to stars and galaxies. Prior to the discovery of the Higgs boson at a large particle collider facility, scientists had theorized about its existence for decades, believing that its presence was essential to validate certain theoretical models known as the Standard Model of particle physics. This model describes the fundamental particles and the interactions that govern their behavior. The experimental confirmation of the Higgs boson not only verified this framework, but also filled in a significant gap in our understanding of how the universe operates at the most basic level. Furthermore, the existence of the Higgs boson raises intriguing questions about the very fabric of reality. It suggests that there could be more to discover beyond the Standard Model, inspiring scientists to explore new theories that might unify gravity with other fundamental forces or even delve into the dark matter and dark energy that permeate our universe. The discovery of the Higgs boson reinforced our understanding of mass while opening pathways to deeper mysteries of the cosmos that remain to be unraveled. New ideas in physics are reshaping our understanding of time in profound ways. Traditionally, time has been seen as a constant flow, a linear progression where moments follow one another in an unyielding sequence. However, contemporary theories suggest that time might not be as straightforward as it seems. One of the most compelling challenges to traditional views comes from quantum mechanics, which reveals that at the smallest scales, the behavior of particles does not always follow clear timelines. Instead, particles can exist in multiple states simultaneously, creating a kind of branching reality. This phenomenon raises questions about the nature of time itself, suggesting it could be interconnected with the very fabric of the universe in ways we are only beginning to understand. Another revolutionary concept involves the theory of relativity, which shows that time is not uniform. Instead, it is influenced by gravity and speed. When an object moves very quickly or is located near a massive body, time can slow down relative to an observer in a different context. This has been confirmed by experiments involving precise clocks placed on aircraft or satellites, which demonstrate time can pass differently based on their conditions. Moreover, some physicists are exploring the notion that time may be an illusion or a construct of human perception. In this perspective, time might emerge from deeper underlying processes in the universe rather than existing as a fundamental aspect. This idea parallels advances in cosmology, where the beginning of time itself, linked to the Big Bang, is a subject of intense inquiry. What did time mean before that event? Did it even exist? These evolving ideas encourage scientists to rethink time from various angles, employing innovative mathematics and confronting philosophical implications. What once seemed a rigid law may actually be an intricate interplay of forces and perceptions, leading to a deeper dialogue on the nature of reality itself. As we delve further into the universe's mysteries, our view of time continues to evolve, challenging the very foundations of physics and inviting us to glimpse a more complex and interconnected cosmos. Throughout history, astronomy has profoundly shaped society in various domains, notably in agriculture, navigation, and culture. In agriculture, ancient civilizations relied on the observations of celestial bodies to establish calendars. By tracking the movements of the sun and moon, as well as the appearance of stars and constellations, farmers could determine the optimal times for planting and harvesting. For instance, the Egyptians aligned their planting schedules with the annual flooding of the Nile, which was signaled by the heliacal rising of the star Sirius. This connection between celestial events and agricultural cycles was crucial for food production and societal stability. In the realm of navigation, the stars have acted as a reliable guide for countless travelers. Long before the advent of modern navigation tools, seafarers used celestial bodies to chart their courses across oceans. The North Star, for instance, has served as a fixed point for Northern Hemisphere navigators, providing a sense of direction and helping them traverse vast and previously uncharted waters. As societies developed more sophisticated understanding of the night sky, they created tools like astrolabes and sextants, which enhanced their ability to navigate both land and sea with increased accuracy. Culturally, astronomy has fueled human imagination and inspired countless myths, art, and religious beliefs. The night sky has often been perceived as a canvas for storytelling, with constellations representing gods, heroes, and significant events in the lives of ancient peoples. Societies across the globe have woven their astronomical observations into cultural frameworks, influencing everything from architecture to rituals. For example, many ancient structures, such as Stonehenge or the Great Pyramids, were designed with astronomical alignments, reflecting the importance of celestial cycles in their cultural practices. Astronomy has not only helped humanity understand the universe, but has also been a fundamental part of our social fabric. From ensuring food security to guiding exploration and enriching cultural narratives, the influence of the stars continues to resonate through time, demonstrating our unbreakable connection to the cosmos. As humanity looks towards the stars for new resources, the concept of space mining invites a host of ethical considerations. One of the primary concerns is the ownership of celestial bodies. Unlike land on Earth, where property rights are established and governed, space operates within a framework of international treaties that are still evolving. This uncertainty raises questions about whether a single nation or a private corporation can claim parts of the Moon or asteroids as their own. The potential for environmental impact cannot be overlooked either. Space is often viewed as a frontier of untouched natural beauty, and the act of mining could disrupt that pristine condition. Not only does this provoke thoughts about the preservation of these celestial environments, but it also challenges us to consider the long-term effects of extracting resources in ways that could lead to pollution or other forms of degradation, akin to what we've seen on our home planet. Moreover, the potential benefits of space mining must be weighed against the needs of people on Earth. If valuable materials can be harvested from asteroids, will these resources be utilized to benefit humanity as a whole, or will they primarily serve the interests of wealthy corporations and nations? This question of equity is crucial, especially when considering how funds and resources could instead address pressing issues like poverty or climate change on Earth. The rights of future generations also play a significant role in the ethical discussion. As we venture into deep space, we must ask whether we are making decisions that safeguard the universe for those who come after us. Would our activities in space create monopolies on resources that limit opportunities for future explorers? Lastly, the potential for conflict cannot be ignored. As nations and corporations set their sights on lucrative locations in space, the risk of competition escalating into disputes or even conflict increases. The framework surrounding space mining must not only address these ethical considerations, but also pave the way for collaborative efforts that prioritize the well-being of both our planet and the cosmos. Space mining opens a complex dialogue that stretches well beyond the mere extraction of resources. It challenges us to think carefully about governance, environmental stewardship, social equity, and our legacy in the universe. Giant observatories like the European Organization for Nuclear Research, known as CERN, play a transformative role in both scientific understanding and technological advancements. At its core, CERN is dedicated to unraveling the fundamental mysteries of the universe, including the basic building blocks of matter and the forces that govern them. By smashing particles together at near-light speeds, CERN enables scientists to probe conditions similar to those just after the Big Bang, offering insights into the nature of the cosmos. The discoveries made at CERN, such as the Higgs boson, not only expand our knowledge of particle physics, but also lay the groundwork for new theoretical frameworks that can shift our understanding of everything from the smallest particles to the largest structures in the universe. These insights can inspire an entire generation of research in fields like quantum physics and cosmology. Moreover, the technology developed at facilities like CERN often finds applications beyond basic research. For instance, the advancement of particle detection technologies has implications in medical fields, particularly in imaging techniques such as positron emission tomography. Furthermore, the need to handle vast amounts of data has spurred innovations in computing and data analysis that trickle down to industries like telecommunications and information technology. The World Wide Web itself originated from efforts at CERN to facilitate information sharing among scientists. Giant observatories like CERN are not only key to answering profound scientific questions, but serve as catalysts for technological progress, shaping both theoretical paradigms and practical applications that benefit society as a whole. Their influence extends far beyond the realms of theoretical physics, igniting new technologies, methodologies, and even ways of thinking, all of which contribute to the advancement of human knowledge and capability. The surge in public interest in space exploration is profoundly influencing both governmental and private investment strategies. Over recent years, a growing fascination with the cosmos, bolstered by spectacular missions to Mars, the breathtaking photographs from distant galaxies, and exciting discoveries about exoplanets, has captivated the imaginations of many. This enthusiasm has shifted public perception from viewing space as a distant and abstract concept to a dynamic frontier that holds great potential for human advancement. Governments across the globe are taking notice of this fervor. Increased enthusiasm translates to heightened public support for funding space missions, which in turn encourages policymakers to allocate more resources. Economic arguments also bolster this shift. Investing in space can spur technological advancements that have practical applications on Earth. For instance, satellite technology has enhanced communication, weather forecasting, and disaster management. As a result, government agencies are looking to not only maintain but also expand their space programs, motivated by both scientific possibility and the potential for international prestige. On the private side, the excitement surrounding space exploration has led to an influx of investments from corporations and entrepreneurs. Companies like SpaceX and Blue Origin are at the forefront, pushing boundaries in ways previously thought possible only in government space agencies. Public interest has created a market for space tourism, satellite internet, and even asteroid mining, driving the need for innovative technology and services. Investors are recognizing that engaging in space endeavors can yield significant financial returns and create new industries, further fueling the investment cycle. As public curiosity continues to grow, so too does the likelihood of collaborative efforts between governments and private entities. This partnership could lead to ambitious projects, such as missions to Mars or establishing a sustainable human presence on the Moon. By capitalizing on the reciprocal interests of the public and the advancements in technology, a new era of exploration emerges, where the shared vision pushes the boundaries of what humanity can achieve in the vast expanse of space. International collaborations play a pivotal role in deepening our understanding of the cosmos. The universe is vast, and exploring its mysteries often requires resources, knowledge, and expertise that surpass what any single nation can provide. By joining forces, scientists from diverse backgrounds bring a rich array of perspectives and skills to the table, enhancing creativity and innovation in research. When countries work together, they can share the considerable costs associated with building and maintaining advanced telescopes, spacecraft, and laboratory facilities. These projects, such as space missions or observatories, often involve intricate engineering and extensive research that demands collaboration to manage effectively. Sharing financial burdens allows for grander, more ambitious projects that push the boundaries of what we can explore and discover. Furthermore, collaborative efforts foster the exchange of ideas and knowledge. Scientists from around the world can share their findings, methodologies, and technologies, accelerating the advancement of our understanding. When researchers convene in international teams, they often combine different approaches to problem solving, resulting in comprehensive studies that span various fields of astronomy, astrophysics, engineering, and even biology. The data we gather about far-off galaxies, mysterious dark matter, or gravitational waves benefits greatly from this collaboration. By pooling data from multiple observatories and using a range of instruments, international teams can create a more complete picture of the cosmos. This can lead to breakthroughs that might not be attainable in isolation. Additionally, international partnerships play a crucial role in building a global scientific community. They help inspire and train the next generation of scientists, encouraging young researchers to learn from their international peers and participate in groundbreaking work. This not only enriches individual careers, but also builds a community dedicated to the shared goal of understanding the universe. International collaborations are fundamental in the quest to unlock the secrets of the cosmos. They enable us to harness diverse talents and resources, making it possible to tackle complex scientific challenges while fostering a global culture of cooperation, innovation, and discovery. Auroras are stunning natural light displays that occur primarily in the polar regions, where they fill the sky with vibrant colors, often shifting and dancing like a celestial ballet. These phenomena, commonly known as the northern and southern lights, are caused by the interaction between charged particles from the Sun and the Earth's magnetic field. The process begins with the Sun continuously emitting a stream of particles known as solar wind. When these charged particles, primarily electrons and protons, reach Earth, they encounter the planet's magnetic field, which acts as a protective shield. Most of these particles are deflected away, but some are funneled toward the polar regions where the magnetic field lines are concentrated. As these high-energy particles dive back into the atmosphere, they collide with gases at high altitudes, particularly oxygen and nitrogen. These collisions excite the gas molecules, which then release energy in the form of light as they return to their normal state. The type of gas and the altitude of the collisions determine the colors we see. For instance, oxygen at higher altitudes often produces red or purple hues, while nitrogen can create the rich blues and purples that add depth to the display. The result is a mesmerizing show of light that can ripple, arc, and swirl across the night sky, creating a spectacle that has captivated humankind for centuries. Viewing an aurora is not just about the visual experience, it's a reminder of the dynamic interplay between our planet and the vast universe beyond, an intersection of solar events and Earth's own atmosphere that culminates in a breathtaking display of nature's artistry. Binary star systems are captivating astronomical structures consisting of two stars that orbit around a common center of mass. Imagine two dancers moving gracefully around each other on a stage. Each star exerts gravitational force, drawing the other toward it, yet their mutual attraction keeps them in a stable partnership. This elegant dance not only affects their paths, but also influences their properties, such as their brightness and temperature. What makes these systems particularly intriguing is their diversity. Binary stars can be classified into two main categories: detached binaries, where the stars do not interact with each other, and contact binaries, where they share material due to their proximity. In contact binaries, the stars can exchange mass, leading to fascinating phenomena like increased brightness or even the formation of new celestial entities. Studying binary systems allows astronomers to unravel the mysteries of stellar evolution. By observing the movements of stars within a binary, scientists can determine their masses more accurately than in solitary stars. This mass data is crucial for understanding how stars live and die, influencing theories about stellar life cycles. Moreover, when one star in a binary becomes a supernova, a dramatic explosion marking the end of a massive star's life, the other star's fate and behavior may significantly shift, creating ripples in the cosmos. Additionally, binary star systems have practical implications, even affecting the potential for planetary systems. Some binary pairs possess planets that orbit one star, while others have rings of gas and dust that might later form new planets. Their environments can vary drastically depending on the star's interactions, making them prime candidates for studying celestial mechanics. Ultimately, binary star systems offer a unique view into the complex gravitational ballet of the universe. The interplay of light, mass, and motion in these dual systems not only enhances our understanding of stars, but also ignites our imagination about the countless relationships playing out across the cosmos. Pulsars are highly magnetized, rotating neutron stars that emit beams of electromagnetic radiation. As they spin, these beams sweep through space, much like a lighthouse illuminating the surrounding darkness. The key feature of pulsars is their incredibly precise timing, which makes them invaluable for both navigation and scientific research. Imagine observing a pulsar from a distance. Each time its beam reaches your location, it creates a pulse of light. These pulses are remarkably consistent, arriving at regular intervals that can be compared to the ticking of a cosmic clock. This reliability allows scientists to use pulsars to measure time with astounding accuracy. The precision of pulsar timing can differ from atomic clocks by only a fraction, making them one of the most accurate timekeeping systems known. In navigation, pulsars could serve as a guidepost in the vastness of space. Spacecraft can use the timing of pulsar signals to determine their position within the cosmos. By identifying which pulsars are visible and measuring the time it takes for their signals to reach the spacecraft, navigation systems can triangulate the vessel's location relative to these celestial waypoints. This method offers a reliable alternative to conventional GPS systems, especially in deep space where traditional signals are weak or non-existent. On the scientific discovery front, pulsars provide crucial insights into fundamental physics. Their behavior allows researchers to test aspects of theories like general relativity. For instance, when pulsars are in binary systems, the interaction with a companion star can reveal effects of gravity predicted by Einstein. Additionally, finding an increase in the pulsar's rotation speed or observing anomalies in its signal can hint at gravitational waves, ripples in spacetime caused by massive objects moving through the universe. Pulsars are not merely exotic cosmic phenomena. They are powerful tools facilitating navigation across the universe and advancing our understanding of fundamental physics. Their consistent timing mechanisms allow for precise measurements that benefit both explorers of space and scientists unraveling the mysteries of the cosmos. Stellar nurseries are fascinating regions in space, often found within vast clouds of gas and dust where new stars are born. Imagine these nurseries as giant cosmic cradles, nurturing the seeds of future suns. The process of star formation occurs when parts of these dense clouds collapse under their own gravity. As the gas and dust come together, they form clumps, which gradually grow denser and hotter. As we observe stellar nurseries, several key features signal the dynamic processes at work. First, we see bursts of light emitted by young stars still surrounded by their natal material. These stars are often much hotter and more luminous than older counterparts. They shine brightly in various wavelengths of light, revealing their presence even through the thick dust that envelops them. Another telltale sign of ongoing star formation is the presence of protostars, which are early-phase stars still collecting mass from their surroundings. They may not be fully formed yet, but they emit radiation that can be detected, particularly in infrared light, which penetrates the dust better than visible light. Additionally, the interaction between newly formed stars and their environment is crucial. As young stars release energy and stellar winds, they can blow away surrounding gas and dust, creating cavities and sometimes triggering the formation of new stars in nearby regions. This interconnected web of activity shows a continuous cycle, highlighting how the birth of stars influences their surroundings and fosters further formation. By studying these stellar nurseries, astronomers gain insights into the life cycle of stars. They learn how conditions such as temperature, density, and turbulence contribute to star formation rates. Each observation helps illuminate the complex processes that have shaped the universe's evolution, providing a clearer picture of how countless stars come into existence across the cosmos. Cosmic seasonality refers to patterns in celestial events that recur with remarkable reliability, such as meteor showers and eclipses. These phenomena captivate and intrigue because they are tied to the relationships between Earth and other celestial bodies, like the Moon and various comets. Meteor showers arise when Earth passes through the debris left behind by comets. As these remnants collide with our atmosphere at incredible speeds, they create bright streaks of light known as meteors. Each annual meteor shower is linked to a particular comet, occurring at the same time each year as our planet orbits the Sun. This regularity allows skywatchers to eagerly anticipate the specific dates when these cosmic fireworks will light up the sky. Eclipses, on the other hand, involve the intricate dance of the Earth, Moon, and Sun. A solar eclipse occurs when the Moon passes directly between Earth and the Sun, casting a shadow that darkens portions of our planet. Conversely, a lunar eclipse happens when Earth comes between the Sun and the Moon, allowing Earth's shadow to fall upon the Moon. The cycles of these eclipses are governed by predictable patterns known as Saros cycles. Each cycle lasts for many years, leading to a series of eclipses that repeat with slight shifts over time. Both meteor showers and eclipses provide a glimpse into the dynamic nature of our solar system. They remind us of the interconnectedness of celestial bodies and the predictable forces at play. Observing these events fosters a deeper appreciation for the universe and our place within it, transforming our understanding of time and space into a cosmic rhythm that can be anticipated and celebrated. The potential existence of other intelligent life forms opens a profound dialogue across philosophy and ethics. First, it compels us to reconsider the uniqueness of human experience. For centuries, humans have often viewed themselves as the pinnacle of creation, a perspective rooted in various religious and philosophical doctrines. However, the discovery of intelligent extraterrestrial life would require a re-evaluation of what it means to be intelligent and the diversity of consciousness. This scenario challenges ethical frameworks as well. How do we treat these potential beings? If they possess intellect, emotions, or even cultures, it raises questions about our moral responsibilities toward them. Should we extend the same ethical considerations we apply to humans? This could mean advocating for their rights or considering their welfare in our actions. Furthermore, the philosophical implications delve into the essence of intelligence itself. What establishes sentience? Is it technological advancement, language, emotional capacity, or something else entirely? By contemplating these questions, we must confront biases and assumptions entrenched in our understanding of life and intelligence. Another layer to this discussion involves our place in the universe. If other intelligent beings exist, it may suggest a cosmos brimming with life, prompting existential reflections on humanity's role and responsibilities within it. Such a reality could inspire cooperation rather than competition, urging us to view ourselves as part of a larger tapestry of life rather than the central narrative. Moreover, the possibility also invites us to reflect on the potential for cultural exchange, knowledge sharing, or even conflict. Would we seek collaboration, or would fear of the unknown provoke hostility? In this light, the existence of other intelligent life forms not only expands our understanding of life beyond Earth, but also challenges us to grow ethically and philosophically, shaping a future where considerations of life transcend our previous limitations. The nature of the universe, whether it is infinite or finite, offers profound philosophical implications that stretch far beyond the realm of science. If the universe is infinite, it raises questions about the limits of human understanding and our place within such vastness. Imagine an eternity filled with endless galaxies, stars, and possibilities. This perspective might suggest that every conceivable event has occurred or will occur an infinite number of times, challenging notions of uniqueness and meaning. In an infinite cosmos, our individual experiences may seem trivial, yet they could also be viewed as part of a larger, interconnected tapestry of existence. Conversely, a finite universe, while seemingly more manageable, introduces other intriguing philosophical questions. In this scenario, one might ponder the nature of beginnings and endings, leading to discussions about creation and the fate of all celestial bodies. A finite universe suggests limits and boundaries, making our search for knowledge and understanding more urgent and significant. It prompts inquiries into what lies beyond these boundaries, if anything exists at all, and how that impacts our understanding of life and existence as a whole. Both perspectives invite contemplation about time, existence, and purpose. The infinite universe implies a kind of permanence, where life may seem transient in the face of eternity. In contrast, a finite universe might elevate the value of individual moments, urging us to appreciate our lives in the context of a limited expanse. Ultimately, whether infinite or finite, the universe challenges us to question our assumptions about existence and encourages a deeper exploration of the mysteries that surround us. The origins of the universe are a profound concept that intersects with various spiritual and religious beliefs, often inviting deep reflection and varied interpretations. At its core, understanding how the universe began prompts questions about existence, purpose, and the nature of reality itself. Many religious narratives provide creation myths that describe how the universe and everything within it were brought into being by a divine force. These stories often serve to explain human existence and humanity's place within this expansive cosmos. On the other hand, scientific theories about the universe's origins, such as the Big Bang, suggest a beginning that is rooted in physical processes rather than divine intervention. This has led to a re-evaluation of faith for some, prompting them to reconcile scientific understanding with their spiritual beliefs. They may view the Big Bang not as a replacement for the divine, but as a possible method through which a higher power expressed creation. an intersection of science and spirituality. Additionally, the quest for understanding the universe has ignited a sense of awe that often resonates with spiritual traditions. The vastness of the cosmos can inspire feelings of connection to something greater than oneself, fostering beliefs in unity, transcendence, and the divine. This sense of wonder reflects a common thread across many spiritual philosophies, highlighting the human yearning to find meaning in the cosmos, whether through the lens of faith or science. Ultimately, ideas about the universe's origins can deeply influence spiritual and religious beliefs, shaping how individuals perceive creation, existence, and their relationship with the universe itself. This interplay invites an ongoing dialogue where the boundaries of faith and reason blend, inspiring a richer appreciation for both the mysteries of existence and the teachings of various belief systems. The idea of the multiverse presents a fascinating challenge to our understanding of individuality. In traditional views, each person is seen as a singular being, shaped by a unique set of experiences and choices. However, the multiverse theory suggests that there could be countless versions of ourselves, each living different lives based on the myriad choices we make. Imagine a vast expanse of universes, each one slightly different from the next. In one universe, you might have pursued a different career, while in another, a pivotal choice led you down an entirely distinct path. This raises profound questions about what it truly means to be an individual. If there are infinite versions of you spread across multiple realities, can we still hold on to the notion that our experiences, thoughts, and feelings make us unique? Are we defined by the life we live here, or do all those alternate selves diminish our distinctiveness? Moreover, the multiverse invites us to reconsider the concept of fate and free will. If every possible outcome is played out in some universe, does that suggest our choices are predetermined? Alternatively, if every decision creates a branching path, it highlights the agency each of us has, despite the existence of other selves. These reflections can evoke both comfort and existential dread. On one hand, the multiverse might imply that we are never truly alone. Other versions of ourselves experience alternate realities that resonate with our desires and dreams. On the other hand, it can evoke feelings of insignificance, as the uniqueness of our existence seems diluted when we acknowledge that countless variations of ourselves exist. Ultimately, the exploration of the multiverse forces us to confront the nature of identity and existence itself. It challenges us to define what individuality means in a reality that is more intricate and interwoven than we can fully comprehend. Our experiences, thoughts, and choices might still hold paramount importance, serving as a thread that weaves the fabric of our lives, while the broader cosmic tapestry teems with other potentialities waiting to be explored. Contemplating the universe invites us to ponder profound questions about our existence and the nature of consciousness itself. When we look up at the vastness of the cosmos, filled with galaxies, stars, and the mysterious dark matter that pervades it, we become acutely aware of our place within this grand tapestry. This realization can spark deep reflections on what it means to be conscious beings in an expansive universe. As we explore the concepts of space and time, we begin to see that our understanding of self-identity might be influenced by how we perceive our surroundings. For instance, the idea that we are part of something larger can challenge the notion of a singular, isolated identity. Instead of seeing ourselves as separate entities, we can recognize that we share our existence with countless other forms of life and matter. This interconnectedness can lead us to reassess our perceptions, encouraging a more holistic view of consciousness that transcends boundaries. Furthermore, contemplating the universe often raises existential inquiries. What is the ultimate purpose of consciousness? Are we merely grains of sand on a vast beach, or does our awareness have intrinsic value? Such reflections can be transformative. They encourage a sense of humility and wonder, fostering personal growth and a deeper appreciation for life, both on Earth and beyond. The exploration of space may also inspire us to think about the mind itself as a map that interacts with both internal and external realities. Just as the universe is ever expanding, so too can our understanding of consciousness evolve. Engaging with these ideas helps to cultivate a sense of curiosity and an openness to discovery, pushing the boundaries of what we know about ourselves. The contemplation of the cosmos illuminates our journey towards self-awareness as we grapple with our significance in the universe and the intricate relationship between our consciousness and the vast unknown that surrounds us.